give it about 5 more minutes, and then we'll kick things off. Thanks.
Thank you.
Machine right now.
Is this now being seen by everyone?
All right, perfect. Yeah, do you want to go up? You can go up to the moderator spot. John's sharing his screen now, so you can tell people to click on it if they want to see the full screen on their computer.
Yeah, so we're
and then also.
So yeah, we're live. So like my audio's being heard. So and live stream. So yep, I'll do it now. Okay,
cool.
Mike,
I gotta put my.
Hey, John, are you there?
yes.
Okay. I'm not sure if folks can hear me beyond just that as well.
I think. Are you standing in one of the circles?
I'm at the podium on the right.
Yeah. Neil, if you could go into the audience and then come back out and see if.
Hey, Neil, can you hear me? I can't hear you. I can't hear anybody.
Yes, I can hear you. How about the slides?
Okay, so now let me go to slide mode. Hey, excellent. All right.
Yeah.
Like maybe John, Mike, and Neil, if you want to communicate over Slack like that, because everything will be visible on in Gather. All right. So okay, folks, we're going to get started in about a minute. So please take your seats, your virtual seats.
Yep.
Just a heads up, if for anybody that's in the audience, if you can't see the screen, there should be a little icon at the top, John Swoboda's screen. If you click on that, it'll bring it to full screen view on your computer. And then we'll step through those slides in a minute.
Yeah.
And yeah, Mike, John, and Neil, if let's say during the presentation, if I cut out audio wise or anything like that, just give me a heads up, like while I'm presenting.
Okay. I'm going to mute myself while I'm doing this,
Perfect.
just because keep the background noise from getting in there.
And if any of you also have like a second screen, or if you want to look at the YouTube live, see if that's also working. It'll be out of sync by about 15 seconds.
Mm-hmm.
Okay, thank you. All right, I guess we'll get started. Yay! So everyone, welcome to NEWSDR 2022, the 12th. I know, 12 years of New England workshop on software-defined radio. It's like that's over a decade, right? So that's definitely been quite the annual event over the last, over a really long period of time, right? So I'm really excited to sort of welcome all of you to this virtual event. Hopefully it'll be the last one, and next year we'll get to be connecting all together in person. My name's Alex Wiglinski, so I'm one of the co-organizers of NEWSDR. I'm also a professor of electrical and computer engineering and associate dean of graduate studies at Worcester Polytechnic Institute in Worcester, Massachusetts. My collaborators and co-organizers and co-founders are Neil Pandia from NI Edis Research, Mike Rain from University of Massachusetts in Boston, and John Swoboda from MIT Haystack Observatory. So we are really excited. Yep, no, please, next slide. Thanks, John. So first of all, first and foremost, like there's a lot of things, there's a lot of folks who support this event, like over the last 12 years. There's obviously the software-defined radio community, the wireless community that surrounds us, that's really excited about this technology that more and more, especially during the COVID pandemic, has really kind of exponentially grown in terms of its way of connecting all of us, especially when we're unable to meet in person. And now we're seeing sort of the impact of that connectivity. So definitely, big thanks to our attendees, our community. Very importantly, our sponsors, and MathWorks, NI, Edis Research, Analog Devices, MediaTek, and Link. Without their generous support throughout the years, this event probably would not be what it is today. And both financially as well as technically, as well as providing these great insights and ideas and helping organize activities that really bring the software-defined radio community together. Next slide, John. Thank you. So a little bit of history about what is NEWSDR. And it's kind of funny because, people sort of pronounce NEWSDR differently, right? The most interesting one that is completely unobvious, but it's somehow my wife instantly saw it, is she says, "Oh, news doctor." I'm like, ooh, that's true. That could read as news doctor as well. And luckily, we have not been flagged by anything saying this is not legitimate or anything like that. But NEWSDR it started in 2011 at Boston U. It was an event. It turned out to be 40 people on a Saturday, just saying, hey, let's just get together, kind of how ham enthusiasts get together, or people that fly remote controlled planes get together, and just saying, let's just spend a day just talk stuff about how software-defined radio technology is. And then it just kind of took up from there. It just began taking a persona of itself, and it developed into essentially where we've been averaging approximately about 110, 120 attendees before we went into COVID mode, right? And then during COVID, it's okay, shucks, we can't get together in person, but hey, we're technologists, right? Video conferencing technology, we're not afraid of that, not whatsoever. And then we went virtual into 2020. And then 2021, and then now, hopefully the last time, because there is that thing about in-person contact. But through all of that, it's just a great opportunity for all of us to come together, to hear the latest and greatest about this technology, and learn from each other about what we're doing, because just that exchanging of information is just really awesome. In addition to that, and we've been trying to get better about it. Sort of this umbrella type of sort of group that Neil and Mike and John and myself have been trying to push is a user group, right? So we're not just NEWSDR, but we try to organize other activities. Last year, we actually organized a software-defined radio education workshop where we brought several, panel, where we brought several folks using SDR in the classroom in order to teach comms, to teach the world around us, the electromagnetic world around us using this technology. And we hope to do more of that. And we have several ideas as well, but of course, as we're transitioning back to whatever normal is, Definitely stay tuned. But we hope to do more of this, especially since everybody's just gung-ho about getting together in person. So really, this new SDR and SDR Boston is like a user group like anything else, just people getting together to really network and exchange ideas, make friendships, right? Collaborate, invent new ideas. And so we are like, here's some kind of candid photos. I'm in 3 out of 4 of them. My apologies. These are all coming from my phone. If you have other candid, like, new SDR Boston photographs, all of you, like, let's say you were at at a new SDR and WPI, and you were with 3 other folks, and you all did some funny faces while holding like a software defined radio. Let us know, send it to us, and we'll maybe we should like post this on the website. Like, here's some candid photographs of from past new SDRs, because community is really important, right? Next slide, please. So as I said, organizers, Mike Rame from UMass Boston. We anonymized Neil Pandia. This is the best that we can do, like that. And also there's a Bigfoot-like photograph as well, where there's a side profile in the woods, and we couldn't really make it to see if it was Neil or not, but the green shirt gives it away. Then there's me, my official portrait, but I don't always look like that, although I might wear the exact same blazer jacket. And then John Filota with one of his toys at MIT Haystack Observatory, which is like pretty awesome. Okay, next slide. So we have a crazy schedule today, and I think it's like, we're always trying new things. We're always trying to think what really provides a great experience for everybody. Because again, you're all taking time out, especially it's like a Friday, in the summer, and everybody's like thinking, I just can't wait to go to Lake Winnipesaukee or go to the Cape, or go somewhere other than being in front of a computer for 8 hours with 100 other like my bestest SDR enthusiasts, right? So after this welcome introduction and sort of overview, we're really honored to have with us Joseph Evans from STR. So Joe, I would say single-handedly has done, back. Thank you. Joe has single-handedly has been such a supporter. I would say kind of one of sort of critical members or driving forces behind SDR in the US and probably in the world in terms of supporting and moving this technology to where it is today. I'll obviously introduce Joe with his biography, but Dr. Evans, he's done he did stints at NASA, at NSF, at DARPA. He was at DoD, at Undersecretary of Defense. He's now as SDR. He was a professor at University of Kansas. That's where we've intersected. He was my mentor. He's now emeritus professor at Kansas, at University of Kansas. He's worked at several companies. He's founded several companies. He's just done so much for our community, and we're really honored to have him. After that, we have several of our sponsors. We have all our sponsors presenting the latest and greatest, and in the technology, what we want to hear about, what is NI or MathWorks or Analog Devices, Link, and MediaTek are up to with respect to SDR. And it's not just hey, here's the latest radio. It's hey, here's the latest radio. It's capable of this sampling rate with this type of filter, and it can pick up these signals, and we're able to demonstrate it with these waveforms and such. The stuff that we really want to hear about. And again, that's all part of that information dissemination. We always want to kind of connect with our community, so we have 13 poster presentations that graduate students from, I think, undergraduate students and others from, I think, about 7 institutions across the United States sharing with us what they're up to with respect to this technology and wireless in general. Then we have networking. We're going to be networking in this interface. So all day we're going to be using this interface, as well as, and this is the first time we're trying it, but we want to really show that there's a greater software-defined radio community out there. So we're going to have 2 presentations about sort of the next one of these events in these 2. So first of all, Air Force Research Lab at AFRL Wright-Patterson, right? They've been running a Beyond 5G software-defined radio challenge that bring together students from across the United States and across the world to compete in a challenge that uses SDR to do something, potentially with 5G, but think outside the box, and the teams compete with each other. This past competition that just concluded I believe there were 17 university teams that participated. So we want to kind of like say, hey, if you're interested in this, here's some folks you might want to connect with. And then the other one is GNU Radio Conference, which is all things GNU Radio and is really awesome. It's a huge event that's also annual. And we'll have somebody from there also present and share with us what's up with respect to that event. We'll then talk about, this is the first time we've tried this, 4 junior faculty members and researchers from the SDR and the wireless community and the IoT community kind of give a 15-minute presentation about what they've been up to. They're like, let's just say, in terms of if you take the derivative of their career trajectory, it's very, very positive. And we believe that, you know, they're all going to make huge impacts. They've already made huge impacts, but even more impacts to our community, and just a great way of connecting with them and them sharing with us what they're doing. We'll have a few networking breaks, but then we'll have 2 breakout sessions with 4 really awesome tutorials or presentations or panels. We have one on government, government funding opportunities from both the Massachusetts and the federal perspective. We'll also have another session with respect to like Spectrum Paint Night, which I talked about a little bit. I'll go in a little bit more detail in a second. We also have these round tables, kind of like, hey, like, let's get together around round tables and or whatever the virtual equivalent is. And they're thematically related. Like, let's say one on workforce development. How can we support the next generation of software-defined radio in innovators and leaders? Or let's say, what's missing in SDR technology? What can we do to make this technology better? And several other topics, like things like spectrum coexistence and like. We also have, in addition to that, we also have another software-defined radio education panel that talk about like, how do we use this technology in a classroom? So maybe next slide, John. So yeah, so and this is about, like, you know, if you're putting this on like a 40-foot by 50-foot screen, that's about accurate in terms of, like, you know, physical representation of Joe or of Dr. Evans. But no, like, we'll be kicking off in a few minutes with Dr. Evans and his opening presentation for our event to kind of kick us off and, you know, provide that energy that will be like, guiding us throughout the rest of today. Then after that, next slide, please, John. Our junior presenters. So we have Maria Zaleva, who's from University of Albany, who is a world-renowned expert already. Like, you know, she's junior faculty there in spectrum and spectrum coexistence and all things spectrum. It's like absolutely fantastic work she's doing. And then likewise, Ryan Bowles from MIT Haystack Observatory with all his work with respect to remote sensing and radar and radio sciences. We also have Nathaniel Friesel from University of Scranton, who is very active in all things wireless. He's also outside of, you know, the classroom. He does a lot of work in the realm of like ham radio operations and the like. And he's very active research-wise including like an NSF Career Award. And then finally, a new colleague of my own here at WPI, Basima Islam, who is like a juggernaut in terms of like Internet of Things technologies. You got to see her lab. Like, she literally takes apart like laptops and shows generationally, like, you know, here's a laptop from 10 years ago, 5 years ago, 2 years ago. And it's just beautiful how you see everything gets smaller and more compact and more advanced. And she's a Forbes 30 under 30 recipient this year. So she definitely has a lot of potential and energy and excitement in terms of this area. Next slide, please. Then, of course, you know, microscript font. These are all the presentations that we'll be having. First of all, initial presentation orally for 1 to 2 minutes. And then afterwards, during the lunch break, networking break, check them out in the poster presentation room. And you can check out what they're doing and like at each of these institutions. So we have 6 institutions across the New England area and 1 from California about, like, you know, everything from radio telescopes to rural broadband connectivity to, you know, radio frequency on chip implementations. So next slide, please. So I mentioned about the upcoming events. We'll have a couple of quick spiels from both the AFRL Software Defined Radio Challenge as well as GNU Radio Conference 2022. That will be happening later this year. And then next slide, please. And then the breakout sessions. So Professor Starobinski John Swoboda, they'll be talking about the STR used for educational purposes. They'll talk about the paradigms used and how it's how that tool can be used in order to really kind of like provide like that hands-on, out-of-the-box experience for students in the classroom to kind of understand how to use this technology and apply it to real-world problems. Next slide. And then, of course, again, we have to anonymize Neil. But then the roundtables, right? And again, there will be a variety of different topics covered, everything from workforce development to spectrum coexistence to are there any challenges with current SDR technology and where we need to go in order to make that, how to solve these like hurdles to make it even more useful, more impactful to today's society. Next slide, please. And then, oh, there's my face again. But this is actually also very exciting, like the future opportunities for SDR innovation. We're going to have John Chapin from NSF, Frank Roby from DARPA, and Joseph Downing from MassTech, so Massachusetts Technology Collaborative, talk about the different opportunities there are for using software-defined radio for doing real-world problems, to solve real-world problems. And so this is going to be a really exciting panel for everybody interested in seeing like how can they like leverage this technology to jump in and really tackle these challenges that our society experiences today. Next slide, please. And then finally, this is pretty cool. This is like there's actually code if you go to the NEWSDR website to do spectrum painting. So you probably have heard like so let's say you have a spectrogram. Frequency versus time, and say what happens if you like over time you allocate energy in specific frequency bands such that if you take the spectrogram you create a face or a logo or words or something like that. Well, this session's for you, and of course it's going to be completely legal. We're not going to be going into licensed frequencies, and we're going to put like happy faces and stuff like in spectrum where we shouldn't be presenting. But Mike McLernan from the MathWorks and John Swoboda from Haystack are going to be running that session, and it's going to be really, really exciting. So afterwards, you could use that code and you can run your own spectrum paint nights. That would be really awesome. Imagine like storefronts where people say, "Yeah, come in with your laptop and software-defined radio, and let's do some spectrum painting." I think that would be a great evening to spend with the spouse. Yeah. So then after that, last but not least, oh no, last slide. That's perfect. Don't forget about like connecting with us. So we have we have a Slack channel. I'm not sure if it's active except around when there's an event, but definitely we have a Slack channel. So definitely connect with us there. Also LinkedIn, we have a LinkedIn group as well that is a great place to really connect with all of us. For networking purposes, you can direct message folks and everything like that. And really, this is all about community. Like we're doing this primarily as a way of bringing everybody together because we are really an active group of folks where the technology, yes, sure, it's a little bit complicated, but hey, it's just wonderful saying, oh, you tried that? Oh, that's really awesome. Oh, you tried that? And really, this is just a wonderful way for everybody to connect and to learn and to grow and build these relationships, friendships, like just ways of really advancing the technology and taking it another decade in. It would be great to do the 20th NEWSDR in a few years from now, and just seeing this like community continue to grow and learn from each other. So with that, I am going to very warmly introduce Dr. Joe Evans from STR. So I'm going to read his biography because that's what academics do. Like we usually have a piece of paper and we're like hi everyone. Now but let me actually bring up I'm going to abbreviate it a little bit because there are a heck of a lot of accomplishments, and but I do want to emphasize the importance of the achievements of Dr. Evans. So you can find also there's a PDF of the program as well as all the information's available online on our website, newsdr.org or newsdoctor.org, whichever one you prefer. But so Dr. Evans is the vice president of STR, and he was the former principal director of the 5G in the Office of the Director of Defense of Research and Engineering Modernization in the Office of the Undersecretary of Defense for Engineering, Research and Engineering. So under his leadership, he was responsible for coordinating the 5G efforts across the Department of Defense, especially their 5G to Next G research and development portfolio. And so in addition to that, he also served as a program manager for DARPA in the Strategic Technology Office from 2015 to 2019. And he started the program called SHARE, which is Secure Handsets for Assured Resilient Networks at the Tactical Edge, as well as the Geospatial Cloud Analytics Program, or GCA. And also managed the Mobile Hotspots Radio Map, SSPARC, which stands for Shared Spectrum Access for Radar and Communications, COMEX, which is Communications under Extreme RF Spectrum Conditions, WND, which is Wireless Network Defense, and Dynamo. Oh, that's a cool one. I love that. Like that, which stands for Dynamic Network Adaptation for Mission Optimization Programs. From 1989 to 2019, Dr. Evans was also a professor at the University of Kansas, so go Jayhawks, in Lawrence, Kansas, and where he ultimately was a chaired professor there. He was Dean E. Acker's Distinguished Professor of Electrical and Computer Engineering. He also served in numerous administrative posts there. And as well, we had a research center called like ITTC, so Information Technology, I forgot the other T. Yeah, so ITTC. So, and also during that time, he also served as an NSF program manager from 2003 to 2005. And he was responsible for launching several programs there under the Directorate for Computer and Information Science and Engineering. Dr. Evans was also co-founder and member of the board for board member for NetGames USA. So it's a network gaming company that was acquired by Microsoft in 2000, and was also a chief scientist at Ascend Intelligence LLC, which developed the Tactical Ground Reporting System, or TIGER, for DARPA and the US Army. And it was widely deployed in places like Iraq and Afghanistan. And also it was acquired by General Dynamics in 2010. And so Dr. Evans is a council member for the Computing Community Consortium Council from 2012 to 2015, member at large for the IEEE Communications Society Board of Governors from 2009 to 2011. And he received his Bachelor's of Science in Electrical Engineering from Lafayette College in 1983, an MSc, an MA, and PhD degrees from Princeton in 1984, 1986, and 1989. And he is a fellow of the IEEE. So with that, let's warmly welcome Dr. Joseph Evans to NEWSDR 2022. And I'm going to try and change the screen to put speaker mode. So maybe, would that be better?
So the lectern there, does that work?
Yeah. If I think like John's off of it, so you should, let me see if I can. Oh, there we go. Perfect. Yep. You're all set.
Okay, and I am also going to try to do screen share for slides, so this will be an experiment.
Okay. Real-time experimentation is always cool.
Exactly. Okay, so we'll try, I think I can see how this might work. Okay, so we'll try this. And then the question is, will it go to full screen mode properly?
There we go. Yep, there we go.
Did that work?
Yep.
Okay.
We're golden.
Okay, great.
Golden. Yay.
Great.
Thank you.
So thank you for the very kind introduction. Really appreciate that. And I really have enjoyed working with this community, the SDR community over the years. I did notice in the audience a number of folks that were involved in various things. And so in particular, I noticed that John Chapin was there. And I wanted to make sure I gave a shout out to him because a couple of the programs you mentioned, DARPA programs, Radio Map and Spark, were started by John. I inherited them, but John started those. So I'll make sure he got due credit for that. So the as Alex mentioned, my most recent gig is working for SDR, which is a Boston area company, but before that was the lead for DoD in 5G, and one of the things that 5G and 6G and beyond, and the one of the things there that I think was really interesting to me was how SDRs have really become the way that companies and integrators, service providers are looking to implement that technology and deploy that technology. So I think SDRs have come a long way from the last time I gave a talk at NEWSDR back in 2013. So I wanted to kind of revisit that a little bit because it's always fun to look at you know, some of your predictions and thoughts from that long ago, 9 years ago, and then talk a little bit about how SDR is being used in defense applications because of my recent involvement with DARPA and you know, Department of Defense leadership, and then a little bit about why. So let's go back to 2013. So back in 2013, I was, oops, did we lose something there? Hold on. So back in 2013, you know, I gave a light lunchtime talk, I think, and it was kind of a mix of SDRs and SDNs and so forth. But one of the things that I did do in that talk is talk a little bit about the history of software-defined radios, ranging back to you know, before DARPA, the ARPA packet radio program, and some of the work that was done there. It was a little bit of software and mostly hardware, but it was you know, it was kind of the first attempt at SDRs. And then there were a series of military systems, and I'll mention one in particular along the way that we were involved with. And then there were a number of other programs. What I would mention was kind of a fun one because it really does go back in history. We at KU we did something called the DARPA as part of the DARPA Global Mobile Information Systems program, and so we did a project called Rapidly Deployable Radio Network. Started in about 1993, 1994, somewhere in there, and ran until 1998 or 99. But it was doing software-defined radios with some beamforming hardware. And as you can see, that graphic on the left is from early in the project, 1994, and it looks, you know, if you look at some of the different bits and pieces of that, it's kind of even interesting still to today. So it's kind of a you know, first dipping our toe into, you know, what you might do in terms of military systems with SDR technology. Back in the 2013 talk, and this was a little bit more of the speculative piece, was looking at you know, how all of these you know, the softwareization of the world impacts radios, networks, and you know, what you might do with those types of systems. And I think a lot of what we discuss here has come to pass. Some of it is continuing to come to pass, but you know, we see networks with more and varied technologies because we have, you know, fiber, different types of radio systems, SATCOM systems, you know, LEOsats and so forth, that really are making the world of both RF and networks, you know, very, very exciting, but increasingly complex. You know, certainly one of the things, you know, working in the defense community and working, you know, with DoD leadership and the National Security Council and so forth, you know, there has been a tremendous amount of concern about the fact that we have added all this complexity. We have made systems increasingly software-based, which, you know, there's concerns about increasing vulnerabilities because of that. At the same time, there's the good news that you know, we have vastly greater flexibility. And again, this was an old slide from that talk in 2013, but what you are increasingly seeing in various efforts, programs and their follow-ons, things like the Dynamo program that Alex mentioned, but also some of the newer programs, the DARPA program called MINC, that was the performers were contract awardees were recently named. Those are looking at these different ways of constructing networks and doing more with the flexibility and the adaptability that SDRs and SDNs are bringing to the game. So that's enough about the past. I want to talk a little bit about where SDR technology is used in DoD and the government and so forth, and some particular use cases. I'll go through at least one use case of where SDRs can bring a lot of value. So one of the things, as I mentioned, that I think is very interesting about 5G and beyond, and the industry players in particular, the service providers, is this trend to softerize and virtualize 5G architecture. Pretty much everyone in the provider community would like to have increasingly virtualized architectures, that is moving, having as little custom hardware on the edge as possible, and then pushing to essentially either regional centers or cloud centers where you're doing radio types of functions. And so there's this architectural split between the radio unit and the distributed unit and the centralized unit. And that graphic on the right tries to, it's too small to really read, but tries to give a sense of some of the different options that the industry is looking at in terms of how you divide those capabilities in order to provide 5G services. This trend, I think, really plays into what the SDR community has been doing, because really what you're doing with these splits is very simple representations out at the radio unit, and then most of the processing at the distributed unit, and then centralized beyond that. There are various efforts to exploit the ability to do 5G in software. There is, the initiative that I started within, Office of the Undersecretary of Defense for Research and Engineering, called the 5G to Next G program, that worked with partners across the government, including our friends at NTIA. And so with some DoD funding, NTIA has been putting on this 5G challenge to start to look at how you build systems with open interfaces. And of course, there's several truly open source implementations. I just cited a couple at the bottom there, SRS and Open Air Interface. SRS has been, been getting funding from various governmental, U.S. governmental sources, Open Air Interface as well, including National Science Foundation and DoD. So I think those are interesting examples of software-defined 5G stacks. This is not an exclusive list, obviously. There are commercial providers, Radisys, many others that are providing great capabilities as well. Just pick these two because some of our funding from OSB had gone those directions. But I really think that it's been very interesting over the years from the early SDR years in the 90s and early 2000s to today. Today, SDR is basically taken as the way to do things, not a research project anymore, but the way to do things. I want to give a particular example of DoD use of SDRs in 5G. So this is a use case that we were exploring. This is looking at vehicular networking, and maybe networking using both manned and unmanned vehicles, semi-autonomous convoys, or maybe the first one's manned and the rest follow the leader, maybe accompanied by drones, which of course, autonomous or semi-autonomous. And all those need to be networked in order to coordinate their activities. Largely, this type of vehicular networking thing mirrors civilian needs, but in the case of the military world, the infrastructure may not always be available. So you need to bring the network with you. So the network itself needs to be mobile. On the lower right-hand side there, you see a picture of one of the Colts, the cells on light trucks that DoD acquired to do experimentation with this type of concept. One of the things you can notice is that light truck isn't so light. I think it's Ford F-550. And so these are beasts, and probably larger than are actually needed for the DoD use cases, where you just have maybe a couple hundred users on one of these cell sites, or maybe even in the entire network, the private network that you're providing. And so the most pressing need for something like this is just something that's low SWaP-C for the network itself. And as we have looked at different options for those types of use cases, SDRs really provide the flexibility to reach these different parts of a trade space. Most of the 5G industry is looking at large numbers of users of the system, large traffic volumes. In the DoD use case, it's a different part of that trade-off space, where relatively small number of users, relatively smaller data use. And so, can we optimize for that? And again, I think SDRs really provide that type of capability. Just as a couple other examples of SDR use in the defense sector, tactical radios. That one on the left is kind of fun. It's SUOSAS radio is one of your earliest software-defined radios done by DARPA in the late 90s, early 2000s. That went to operational use. And then on the right is one that is in very common use throughout the military, PRC 117 Golf, that is used by the Marine Corps, the Army, and it is a software-defined radio, and probably has capabilities beyond what DoD typically uses, simply because it does have that flexibility to be adapted. The other place where SDRs are used in the defense sector is in radars, software-defined radars, and this is just a picture from a non-military, definitely non-military SDR based radar, but you can think of similar types of systems that DoD might be using and experimenting with. I should say that I had good pictures of such systems on my government computer, but we'll have to settle for something from the web for this talk. So just this is probably obvious, but just wanted to talk a little bit about why SDRs are so interesting for defense applications. First of all is the flexibility to rapidly create new capabilities. So one of the things that we were exploring is how do you modify a 5G radio stack to provide features that might be useful for various different types of applications. So for example, can you modify the beamforming algorithms in order to provide ways to null out interferers or something like that, which also gets us to the second piece, which is that the software-defined radios are also more easily made adaptive or adaptable. So as requirements are learned in real time, the system could be changed to fit circumstances. So not only might you have the ability to null out and interfere, but maybe you might be able to change the waveform in real time, or the beam pattern in real time to mitigate interference. So that type of flexibility down at the RF level is tremendously valuable to the military. And finally, one that's maybe a little less obvious is that SDRs can be cost effective because the military often needs systems in smaller quantities than the commercial markets. One of the things that I always pointed out, in my job with OSD, is that civilian markets are just massive compared to DoD. So, for example, I think it was Samsung had a research budget of around 19 billion, R&D budget of 19 billion in 2019, and there's never been a DoD comms program of that size. So our SDRs do provide the ability to create systems in smaller quantities and find a relatively generic hardware platform that can support many different use cases. And so just to wrap up, we think SDRs are well suited to defense applications. Certainly our 5G to next G effort did emphasize this, provide greater flexibility and adaptability, and as I said, a good fit for the defense market size. There are risks of having these software-defined systems, but these are inherent to all software systems, and the flexibility and adaptability and cost-effectiveness benefits far outweigh that. So with that, I will hand it back to Alex.
Oh. I'm not sure how like 100 people are in the room would clap all at the same time, but no. But I think I'm channeling that positive energy. No, thank you, Dr. Evans. I think we have time for one or two questions. So I think there's already. Oh no, that's just Mike. So if you have any questions, you'll need to go up to the top left. The left of the podium that says Q, like on the carpet, Q here for Q&A. So if you have any questions, then you have to go position your avatar on top of the green megaphone. So if anyone has any questions, please come on down. Actually, that's the thing. We should have like a Price is Right kind of theme or something. Come on down, we got a software-defined radio. Okay, so I think we have. So we will have time for one or two questions, and I'm not sure if there's like time afterwards offline for folks to connect with Dr. Evans, but yeah, like if anyone has a question, like please go on to whoever gets there first, like green megaphone, go, yay. Okay, we have Mark Fosbury from MITRE, at least that's what the label says. So Mark, take it away. What's your question?
Good morning, everyone. I'm glad to be here. This is an exciting opportunity for me. And this question I have is sort of a naive question. I'm looking at solving a problem in an easy way and going, that should just, so it's a general question. With software-defined radios and firmware, there's a new opportunity to have partial reconfiguration built into the system. So you can have multifunction in a fast way. And I don't know if anybody's been working on it. The example would be as if you could draw a big box around your firmware, your I/O is going to be IQ streams for your ADCs and DACs, and then you'll have data coming in and out the bottom. So if you're going to be a comms radio, your modem would be the data coming in and out the bottom, and your modem functions will be in the box. You can change that out to be radar, where your radar processing will be inside the box, and you can send your results out the data path. So that's sort of my question. Has anyone been thinking about how to handle multifunction and partial reconfiguration so I don't have to do the work? Thank you. Over.
Thank you.
Sure, I can speak to that a little bit. So one of my colleagues at DARPA in the Strategic Technology Office, Ted Woodward, who's also, by the way, associated with the 5G, OSD 5G effort, Ted started a program called Concerto, which was looking at multifunction RF systems. And, that's a relatively mature program now. But looking at both, across the system from, how you build the front ends and so forth. But one of the big problems was resource management. And so there's a big focus on understanding, how you manage the RF front end, as you're mentioning, how you drop in one capability versus another, how you schedule all that. So like I said, it's a fairly mature program, but I forget now who owns the program at DARPA. Programs get inherited by other folks, but it should be available on the web page, and you probably reach out to the PM there.
Cool. Thank you. I'm gonna if there are any other questions, like a short question, I think we can entertain. Otherwise, we'll like any short questions. Nope. I think I just see a lot of like stationary avatars. So with that, Dr. Evans, thank you so much. Hopefully you'll be around the rest of the day. With the arrow keys moving around, but no, definitely. Thank you again for the really insightful presentation, especially showing kind of that like the history, especially from a snapshot of 2013 and now how things have evolved. But very insightful, and thank you again for kicking things off with such a great opening talk. So thank you.
Great. Thank you for inviting me. I really enjoyed it.
Thank you. So with now we are going to transition to the sponsor talks, and the order in which we'll be having the sponsor talks is we'll start off with NI and EDIS research, followed by MathWorks, Analog Devices, Link, and then MediaTek. So first up, we have Hayden Nelson from NI EDIS research to present the latest and greatest from them, in terms of hopefully there's like a USRP X 1000 or something, forget about going every 100, just make the quantum leap, this
I don't have a big hardware announcement for you today, Alex. I'm sorry to disappoint. I guess first let me check. Can you hear me okay?
Oh yeah, I hear you. How about the audience? Can everyone hear Hayden?
I found that down there at the bottom of your screen, there's a little smiley face that has reactions, that has like little hearts and like applause. So in the audience, you can do thumbs up and things like that.
Oh,
there
cool.
you go. Oh, look, they found all the thumbs up. So that means they can hear
awesome. You know what we should do is make a wave of thumbs up. Just like at a stadium, it's like we start at the top and we make a wave. Yeah, exactly. We'll coordinate that afterwards. Maybe we'll use some software-defined radios to talk amongst ourselves and say, okay, no, just kidding. So again, we're very honored to have and the support of our sponsors, including NI and EDIS Research, MathWorks, Analog Devices, Link, and MediaTek. So with that, Hayden, thank you, and the floor is yours.
Let me share my screen here. I appreciate it, and again, we're excited to be here. Looking forward to getting back in person. I was been taking part, so for the faithful who've come here, y'all probably recognize me. And again, always a great honor to get to partake. So I'll try not to make this. I'll try to do this pretty quickly. I know sponsor talks, you feel like you're going to be sold to or something, right? So my name's Hayden Nelson. I'm a solutions marketing manager for NI and EDIS research. I kind of have multiple jobs. Really passionate about this technology and have a great time. Supporting all the engineers using it out there. So I also manage edis.com. So if you ever see any problems with the website, hayden.nelson with no E in my name at ni.com, feel free to email me direct. Or if you have any questions, I'm always happy to help out, this community. I am from Texas, but I worked at Lincoln Labs years ago. So I have some Boston connections, but I still have a pretty southerny Texas accent. So I apologize. So I live in Dallas, Texas. Well, anyway, so I just wanted to give you all a brief overview of, I have a lot of slides. I'm going to kind of go fast, but I think I need to stick to about 10 minutes if I'm not mistaken, Alex. So I just wanted to give you all an update, what's new with software-defined radio at NI and EDIS Research. And Dr. Evans, I actually appreciated one of your mentions in there around open air interface and Eurocom, because I'm going to talk a little bit about that. And so last year I came here and I talked about this new radio that we released, mid last year. It's kind of our Lamborghini of a radio. It has a lot of upgrades, to previous generations of USRPs in terms of, bandwidth and channel counts and frequency ranges. And we've seen over the past year a number of engineers taking this and building out capability. So when I announced it last year, it was like brand new. When you're developing any software project, you want to get the minimum set of features built into the driver of said product before you release it. So what we've been working on over the past year is a lot of good upgrades to our driver tool stack around this radio. We now support. Last year, I think I had a little asterisk that said, "Oh, well, this feature's coming, that feature's coming." Like we recently released the latest version of USRP hardware driver. You can go to GitHub and build and install that. We support 100 gigabit Ethernet now on this radio, so that gives you this ability to. The initial release of this radio had this wonderful feature of it had lots of bandwidth. So if you're looking at 5G networks and you're wanting to do these massive amounts of resource blocks and wideband signals, this radio could do that. If you wanted to stream all that data off into some server that could handle that amount of data, well, it was kind of like the old drinking hooking up a fire hose to a garden hose, so to speak, that it was just a lot of data coming in and we didn't have a way to get it off. Well, we've upgraded our driver to support 100 gigabit Ethernet, and that's going to unlock that ability to stream a lot more data off this radio. And so that's new. And there's a number of other upgrades on the UHD that I won't go into for time, but so that's kind of the big product updates is the continual improvement of our open source drivers for this particular radio and all of our other portfolio of radios, which if you're here, you probably know Edis Research, the Edis Research portfolio. So one of the things that we've been investing in is kind of what you talked about, Dr. Evans, was this usefulness of these open source tool chains for kind of virtualizing networks and communications. And in this organization Eurocom, we've become a strategic partner with Eurocom to work with them on open air interface. And what we've done is we've started to build out an open air interface reference design. So Dr. Wiglinski, I had the honor to get to meet some of your undergraduate students about a month or so ago at Wright Brothers Institute in Dayton, Ohio. We sponsored this, and I took part in the something I'll talk about later, the AFRL SDR Challenge, where we sponsor a bunch of AFRL sponsors, and we support the Air Force Research Lab doing this academic challenge where a bunch of students come in. I'll talk about it a bit later. Dr. Wiglinski's three undergrad, he had a big team of undergrad students, but three of his undergrad students came to the finalist competition. And one of the things they did is they actually used open air interface to do this really cool thing where they built out a network, had a G-Node B and a user equipment. And I thought it was really creative and kind of scary because as we look at using 5G in defense applications or security applications, one of the things that group did was they actually built an ability to jam out a single user. So like if you're familiar with an LTE, not LTE, but a 5G new radio, OFDM frame. So it's, frequency and time. And they were able to break into the network and put in a single kind of OFDM block of energy to jam out just a single user. So if somebody were trying to upload their cat videos to YouTube using a 5G phone and they didn't want to see that cat video, they were able to jam out a single user, and they used OAI. And I was like, wow. And these are third year, I think they were third year or seniors, undergrad students. And I was just really impressed with these young engineers using the tool like OAI, and it's a pretty complicated tool. And I walked up to one of the students and I said, hey, and they were using Edis Research. I think they were using B210s, the USB radios. And I said, well, how was it working with OAI? I've heard some people, have a hard time getting up and going, and, but it's a really powerful tool. And he was like, oh yeah, it's we had all this challenge. It's it is open source. And I was like, oh, that's good, because we're actually, if for the future people that had some of those getting up and going challenges, one of the things that we're investing in is working with OAI to build what's called an interface reference design. And what that'll look like is there's a lot of pieces to an SDR based 5G network. and a lot of it is not NI Edis Research products. There's, you need to have the right servers. You need to have, some of the different accessories. There's lots of the software stack, so as you can kind of see here, that, level 1, level 2, level 3, that all kind of come from that's the value of this open source, OAI software stack. But, we're working to make sure that our driver stack plugs in really nicely to that, as well as just recommended configuration and getting started guides and documentation. So, Dr. Wiglinski's students don't stay up till 2 a.m. Working on their next AFRL SDR. So that's really for the sanity of your students, Dr. Wiglinski. But this is something cool that we're working on with Eurocom. The other thing is we've seen a lot of people wanting to use that X410 radio for just recording wireless signals for like wireless sensing, environment sensing, and a number of applications around communications. And we've, one of the wonderful things about SDR is software is in the first word in software-defined radio, and that allows you to work with all kinds of different software tools. Open source things like GNU Radio, Open Air Interface, these type of tools tend to be on these open source tools. We are National Instruments, so we do have this other tool called LabVIEW that we've been building a reference architecture for recording and playing back multi-channel wideband signals with USRPs with LabVIEW. And that actually, the architecture kind of looks like this, where you can have multiple USRPs. LabVIEW works such that you use oftentimes you'll use a PXI chassis and use PCI Express interfaces versus 100 gigabit Ethernet. And the nice thing is we support both of those interfaces on these radios. And so we're building this reference architecture that allows you to get up and going for doing these kind of record and playback type applications. But this tool was built on LabVIEW, and it includes a number of different software tools for being able to create 5G new NR waveforms and use the different libraries. There's a pretty rich set of IP out there, but that's a reference architecture that we've been working with, and we've had our number of users will use these PXI chassis where they'll stream it to the chassis peer-to-peer over and have in-chassis hard drives, so you can build these systems out where so say you're trying to monitor the performance of a network to optimize it for some research project. Well, this is a pretty good way to gather that data and be able to analyze offline. In addition, it turns out that that sometimes these new networks are operating at frequencies above 8 gigahertz, and we do support the option to use millimeter wave extension heads to bring it up into much higher frequencies if that's what's needed for the network of which you're testing against. And so it kind of looks like this in terms of providing some examples for getting started, user interfaces, etc. And so here was some technical specifications for that. In terms of the amount of IQ recording rates, and we have the ability to go to higher than 4 terabytes, but you'll have to use external per 4 terabytes per module. So anyway, and I also talked about this a little bit last year, was this radar EW reference architecture. So Dr. Evans, you talked, I can fully concur that people are using SDRs for radar as well. We actually had a copy of this 2 weeks ago at an event in Austin where we were doing a multi-channel beamforming radar sensing using open source USRPs. And so this is an open source architecture. One of the downfalls of things that people ask for is multi-channel, and not every radio supports multi-channel because it would make it kind of multi-channel phase coherent operation. So it would add to the cost and make the radios too expensive. But we do have a number of radios that we optimized for multi-channel phase coherent applications. And one of them is our USRP N320. So that's kind of the radio we use here, and we're able to phase coherently tie multiple radios together to do a phase coherent radar application. So you can do like radar prototyping, EW prototyping. We call it the open architecture for radar and EW research. I talked about this last year if you were here. This is officially released, and we've continued to upgrade and add bandwidth and features to this. You can go to edis.com, and in our support portal, there's a nice a white paper or an application note on how to set this up. It's all free and open source software, has documentation, just shows you how to build it out. It's just obviously it's based on our radios. And that it's based on these N320s and N321s. And it allows you to, lots of people have tried to do this and some have succeeded, some have had challenges. And so we just said, hey, well, if people are trying to bake these cakes, let's give them a nice recipe so they can bake that cake and make it, make the same tasty cake every single time. And so we've provided all the documentation, the recipe to build out these multi-channel phase coherent systems with this particular radio. And then the other, actually, I do have a new radio to announce to you, Alex, but it's not from NI or Edis Research. It's actually from a company called Curtiss-Wright. We partnered with Curtiss-Wright. So for those of you in the defense space and you're saying, oh man, I love these USRPs, but I have to do all this ruggedization if I'm going to deploy it into a combat environment or a harsh environment. We worked with a company called Curtiss-Wright, where we actually ported the USRP E320 to something called 3U VPX. And so for those of you in the defense space, you're probably pretty aware of what this is. But this is now a possibility with USRPs. And our strategic partnership with Curtiss-Wright is that we support the software. So UHD is supported on this particular module. And this is a picture here from 2 weeks ago in Austin. We hosted Curtiss-Wright at an event, and we were doing a demo using 3DB Labs Scepter software on both their radio and our radio with the same driver versions. Anyway, that's also a cool thing. And then the last thing, I'll continue to plug the AFRL SDR Challenge. We're now open for proposals. Alex, your team did way too well, so you're not allowed to apply. I'm just kidding. Here's some. If you're watching this right now and you're interested in this, reach out. You can reach out to me directly, or take a screenshot right now and hit print screen and open Paint and copy paste this slide. And you can reach out to Tony Liza at Wright Brothers Institute. So AFRL is a defense organization, but they partner with a nonprofit right off base at Wright Brothers Institute, and they will do. AFRL supports mentorship of students. Neil Pandya and I will do training and helping those students along the way to build out their research project. And here's just a picture of some of the great research and projects from last year. We had our finalists. Fortunately, we got to do it all in person down at Wright Brothers Institute. You can see there on the center and the left, that was Dr. Wiglinski's students, and you can see all those radios on the table, running open air interface. Is a number of really good showings from Texas A&M and many universities. And so, but anyway, I just wanted to encourage you, if you have professors in the industry, it's a really great opportunity to get some free USRPs, because AFRL will just donate them, and access to some really talented engineers to help those students get inspired by what you can do with software-defined radio. Anyway, that's all I got. I think I went over, Alex, but let's connect. Stop by the virtual booth, and I'll be around all day to chat.
Thank you, Hayden, and also for the kind words about my team, and let's just say that the 2022-2023 team, they're gonna. I've been telling them this is your bar. You gotta go up.
Yeah, and I have to a very, very high honorable mention of Dr. Rhyme from you. They showed up. They win the award for the most equipment brought. They had all these. They did this light interface, light communication demo there that was really cool with robotic, things, and it was just a neat example of SDR. We talk about wireless, but they're using light, which technically is wireless. It's still electromagnetic waves, but it was really cool to see just the neat ways that it's very open. Do what you want. We don't have too many constraints on it. So anyway, I'll hop off. Thank you for the opportunity to speak.
Awesome. Thank you, Hayden. Thank you. So next up is Mike McLernan from the MathWorks. Come on down. So I think, Mike, you probably have to come to the podium in the front if you're not. Where are you? Yeah, there you go. So yeah, you're gonna have to go past the chairs. Don't hit your knees on any, like that's the thing. Whenever those conference chairs always are awful when knees collide into them. There we go. So Mike, audio check. 1, 2, 3.
Hello. Can you hear me?
Awesome sauce.
Can you see me?
Yep. Thumbs up for everyone. Can you hear Mike in the room? Yep.
I see some thumbs up. Yeah, looks good.
Awesome. So Mike, and let's see if you can share your slides if you have any.
I do indeed. Let me see if I can do this. All right.
Oh, wow.
So
It's a picture in picture.
yeah.
All right. So Mike,
Can you see some slides?
Take it away. Yep. Looks perfect.
All right. Thank you so much. Well, it is a delight and an honor to be here. I've been associated with NEWSDR for, I suppose, the better part of a decade. Lots of good friends among the participants here. Thank you for coming. It is lovely to be here. So I'm going to talk a little bit about who MathWorks is and what we've been doing, not just really in the SDR space, but more or less in the wireless comm space. So I'm going to expand a little bit beyond SDR because we do a lot more than just SDR. Hopefully, many, perhaps all of you have heard of us, but if you haven't, we'll tell you more about who we are and what we've been up to. So there's a picture of our campus. What our aim is globally, worldwide, in many domains, is to accelerate your research and development. We want to build tools that will enable you to get your work done faster, better, cheaper, with more reliability. So we've been around for over 35 years. We build MATLAB and Simulink. Probably many of you have used or still do use it today. For that, we are grateful. What's our mantra? Accelerating the pace of discovery, innovation, development, and learning in engineering and sciences. We do have offices all over the world, the better to serve customers that we have all over the world. There are over 5 million MATLAB users worldwide. So once upon a time, I tried to figure out how many engineers are there in the world. I wonder what percentage of engineers in the world use MATLAB. I failed miserably. If any of you know who or how many engineers there are in the world, I'd love to have that number to see the percentage. But we are also very committed to universities. Actually, I had the privilege to participate at some level in the AFRL Beyond 5G SDR Challenge. Really outstanding work by so many participants. I tip my cap to so many of the teams. Great work there. So what is this eye chart? This is a list of our products and services. Guess how many people in the world know in any depth about all of them? You're right, it's 0. None of us. But the point is, we are involved in many, many different domains, not just in wireless, but so much. Signal processing, artificial intelligence, seismic processing, education. The list is almost endless. I get dizzy just reading it. But a little closer to home, what products do we have that you might care about? First of all, in the signal processing world, you see this list. So we do work in audio and more recently radar. We've talked a little bit about radar even this morning. So we have tools for you there. Wireless communications, which is very near and dear to our hearts. You see this list. We've been investing a lot recently in SATCOM. But very recently, we have introduced a new Bluetooth toolbox and a wireless test bench, which is quite SDR based. We'll talk a little bit more about that in just a few minutes. A lot of work in RF and mixed signal. So the idea is MathWorks is doing all that we can to integrate software modeling and hardware across an entire transceiver. If you're talking about A to D modeling or synchronizer loops or antennas, we really try to get the whole end-to-end link into the simulation. Also, towards that end, a little bit more hardware focus in the RF and mixed signal world. 2 new products in the last year since the last time we all gathered here, RF PCB and signal integrity. So we're trying to serve not only the wireless market, but the wireline market, the backplane communications market. And then finally, if you're talking about going all the way to hardware, many products that deal with HDL automatic code generation for multiple applications. You see wireless, vision, DSP, tools to help you go from floating point to fixed point, and then finally, actual hardware and device modeling with SoC block set. So this is a space that probably is a little bit closer to your all hearts and day-to-day workflows. Love to talk with any of you about any of these products later today. All right, something that we have been starting our investment in, if you will, roughly a decade ago, and just continuing and accelerating since then, is modeling standards. Whether it's 3GPP, whether it's connectivity standards like Zigbee or Wi-Fi or even UWB, which has had another renaissance in the last few years, Bluetooth, as I mentioned. Also, again, SATCOM, DVB-S2 is an amazingly popular waveform used for a whole lot more than just video broadcasting. We've increased our investments in GPS modeling as well on both the waveform generation and the receiver processing side. So we want to be about standards because that's what people are doing. They're not just building QPSK systems. You all are building standards-based systems, and so we want to serve that market very efficiently and effectively. So something that we've made considerable investments in the last 4 or 5 years is essentially codeless wireless waveform generation, whether they are homegrown custom waveforms, OFDM, what have you, or 5G, or Bluetooth, or Wi-Fi. So the idea is that you simply parameterize your waveforms, say with the panel on the left, click generate, and then bang, you have a waveform. And then if you want to take the code that was used to build that waveforms, you would export and generate the MATLAB scripts. So then you can tweak it and tune it to your heart's content. We have realized customers care a lot about this because it's all about accelerating the pace of development and design. So this app has been very, very helpful for many customers in that realm. We seek to model, as I mentioned before, full length. So here we have a very notional, very generic transceiver with a transmitter, channel, receiver. What do we do to seek to serve you in all of those realms? First, as we mentioned before, lots of easy to build waveform generators across all these standards. If you want to build your own homegrown MIMO or OFDM systems, you can do that as well. One of the things that we have tried to do in the wireless world is to give you content that has open MATLAB code in it, because customers have screamed for years, we need to be able to debug, to extend, and to inspect the code that you write. And so that's what we have done. So you can dig down as many layers as you want. And really, if you have a synchronizer loop that works better than ours, take ours out, put yours in. If you want to do beamforming, which is part and parcel of any modern communication system, there are entire products devoted to that endeavor. Antenna modeling, same thing. One of the joys that you can do with antenna modeling is you can actually take a picture of a particular structure that you have and then analyze it in MATLAB with S parameters, with antenna patterns, with resistance over frequency. Very, very detailed and broad analysis for antennas. RF and channel impairments. I'd love to talk about this more, maybe at lunchtime or one of the networking breaks. We can talk about that a little bit more, because if you're going to eventually go to hardware, you need to anticipate what the impairments that you're going to encounter are. And all those impairments are available in software for you. And then if you're going to impair your signal, you have to be able to correct for them. So we try to offer capabilities for synchronization loops, for recovery of carrier offset, for DC blocking, etc. And then finally, you have to be able to measure what you've got. If you're going to have a device that you're building conform to a standard, you have to be able to make measurements like EVM and ACPR. We seek to offer those capabilities as well. So again, the entire simulation and design and test bench portion of your workflow. An area that we have been investing in for, golly, I'm sure it's 20 years, and it's not stopping, is channels. Because if you're building a receiver, it's part and parcel of the work. You have to model the channel. But typically, you don't. It's a necessary evil for a transceiver designer. For us, it's our day job. And an area within the channel modeling world that we've invested in a lot recently is with ray tracing, where we've been working in reflection and getting that as fast as possible. We've been investing in diffraction. We do include buildings, terrain, so that you can do a very fine-grained RF propagation analysis. You want to wonder, well, where do I put my towers if I'm building a cell system? This can be very useful towards that end. With these capabilities, you would get coverage plots. And you would also be able to generate an impulse response so that you can see, okay, if I actually want to filter my signal with my with the channel that my ray tracing analysis gave, you can do that. And then get scatter plots that look essentially like a swarm of gnats clustering around on a summer evening. If you want to learn more, search just channel model. Another thing that we have been investing in recently is modeling comms networks. And our strategy so far has been to simply understand that different standards-based systems, they have their own way to specify networks and to build networks. And so we've tuned our development in network modeling towards standards like 5G. And this is simply a list of examples that portray different aspects of a 5G network. We've done the same for Wi-Fi and ditto for Bluetooth. The point is, there's a lot of research and development that goes on above the PHY. And so we've recognized at MathWorks, we have to be able to model that and offer kind of an integrated PHY and Mac level of simulation for you. So that's something that we've been working very hard on in recent years. Another real area of investment is AI. So there will be a lunchtime session where we'll talk about some recent work in AI about that. And really a shout out to you, Alex, and all the NEWSDR organizers. We really got the motivation and the aha moment to really invest into AI for wireless at a NEWSDR conference. So this would have been 4 or 5 years ago. And it was really eye-opening for us. We said, we've got to jump into this pool. And so we have, and we're not stopping. In the most recent release, we've developed a couple of new examples that talk about digital pre-distortion and beam selection. And in fact, we will be discussing the DPD workflow at the lunchtime session. And I'll offer kind of the punchline now. And that is, with a neural network, digital pre-distortion network, we can actually do better. That's the spectrum in red versus a more historical, traditional memory polynomial. This is a big deal. And so we want to see, are there other areas where AI can afford performance better than what the traditional model-based designs can offer? Finally, this is, after all, an SDR conference. MathWorks does connect to SDRs. So with you can test signals, you can prototype radios with HDL code generation products that I mentioned earlier, and we've been working very hard on performance. So your performance that you experience with the USRP is getting progressively better with 22A and even into the upcoming release of 22B. What radios do we support? USRP certainly, RTL, Zinc, and Pluto. We love all those radios. I like to tell friends of mine, I love all my kids equally. We love all those radios equally. They're just good for different purposes. If you want to learn more, just search on MATLAB SDR. Finally, I mentioned a little bit earlier about wireless test bench. So this is all about intelligent and fast data capture. So I'm going to give you a little bit of a lay of the land here when it talks about transmit and capture speed. If you need to do something, say with up to a 30 megahertz analog bandwidth signal, and you want to use MATLAB, So you can just use our so-called hardware support packages. So with the radios that you saw just in the previous slide, if you have Communications Toolbox, get the support package for free. That's pretty lovely. If you need up to a 5 gigahertz analog bandwidth, well, you're looking at industrial strength instruments like the NIVST, Keysight Tektronix boxes, but you are going to pay a lot of money for it. But there's a middle ground where you don't have to spend quite so much. And this is where the new wireless test bench product comes into play. So do you need to capture, say, up to, say, 200 megahertz of analog bandwidth? Then for a much lower price than 100K between NI software, these are the N300 radios, which are between $15,000 and $20,000. $5,500 for the wireless test bench software. You can get a whole lot of data for spectrum monitoring, spectral conformance work, signal intelligence operations. So these are, we believe that that fits into a very nice sweet spot where if you don't have infinite budget, but you have bandwidth needs that are greater than a few tens of megahertz, this slots in very nicely in that area. And if there are educators in the audience, and I believe there are, we do offer a lot of educational resources. So a few years back, a dear friend of ours at MathWorks, Corey Prust from the Milwaukee School of Engineering, developed a course, an entire semester course for a first level analog and digital course that is littered all throughout with SDR labs. Very, very well-received course. I continue to be amazed at how frequently it is downloaded from the MATLAB file exchange. These are the kind of areas that it touches. Just search on Intro Comms Course File Exchange to learn more. Our summary, MathWorks wants to serve you by providing modeling and hardware connectivity for an antenna-to-bits workflow on the desktop and on the radio. And with that, I thank you very much. I'll turn it over to you, Alex.
Awesome. Thank you, Mike. Thank you so much.
Sure thing.
Thank you.
Absolutely.
So what we're going to do just for the sake of logistics is so a couple of things. So one, we'll have some Q&A at the end for all our sponsors, like questions about what they just presented or what the future lies for like various products and such. The second thing is that thing I mentioned earlier on in this workshop with respect to Slack, right? The Slack channel, which is a type of messaging type of platform that folks use. There's already conversations starting there. That's a great way of folks who are really interested in connecting to actually use it to ask questions like while we're talking. So in fact, there seems to be one conversation happening in the SDR-Boston channel. We also have a NEWSDR-2022 channel as well. And so there are a lot of conversations happening there. So you can do that if you don't want to sort of say it over gather, but rather if you feel more comfortable typing. But if you do want to ask questions like live, we'll have Q&A at the end of this sponsor session. So I just wanted to bring that up. All right. So next up is, and we're not sure about. So like we haven't. There might be some delays, but is anybody from Analog Devices in the house to present their sponsor presentation about the great things that ADI have for the outside world? Anyone from ADI? If not, then we could switch gears. Like I think I see Tomohiro is present, like who's next on deck with respect to Link. So maybe if there's no one from ADI, we'll switch gears. Tomo, are you ready? Like come on down. Okay. Thank you, Mike. Thank you. All right. So Tomo, audio check. 1, 2, 3.
Hello.
Hey. Okay, I can hear you. How about the audience? Thumbs up if you can hear Tomo. Ah, excellent. Awesome sauce.
Thank you. All right. Let me check my camera. Looks like my camera is not working, but probably I can do just with the audio.
Oh,
Cool.
I mean, if you want, if like, I think there was kind of a blacking out, so maybe it was taking a few seconds to initialize, or there's a piece of tape over it. Like that's usually what happens with me. Usually my webcam either it's like the drivers are not quite right, or I just have like the little thing that's blocking it. But yeah,
Right.
yeah, it doesn't look like.
Yeah.
Oh well.
Okay.
Well, so with that, like, I mean, let me warmly introduce Tomohiro Arakawa from Link. And Link
Hi.
do great things with respect to 5G and satellites, and then combining the two worlds together. So we're really excited to have Link here. So Tomo, the floor is yours. And thank you again for supporting NEWSDR.
Thank you. Hello, everyone. So my name is Tomohiro Arakawa. So I'm a SDR engineer at Link, which is building a network of small satellites. So today, I'm going to share a little bit about what we do and what our technologies are. And also, I'm going to talk a little bit about how we use SDR in our satellite systems. All right, so I think we all know the pain of disconnectivity. Like you may be hiking, or you may be on a boat in the middle of the ocean, or you could be camping in a remote area, or you could be working at the farm where there's very little to no cellular coverage. So like in today's society, where we, everyone has connectivity almost all the time, I think we all share the same pain of not having a connectivity in those kind of scenarios. And maybe you're in the places where you usually have cellular terrestrial connectivity, but there may, when the disaster hits, for example, maybe a tsunami or an earthquake, or it could be a wildfire, or it could be flooding. There may be situations where a quick SMS or a phone call might save lives. So at Link, we believe that it is really essential for everyone to stay connected, no matter what happens. So one of the solutions to such disconnectivity issue is the satellite connection, so satellite wireless network. So, today, the cellular network and the satellite network, the satellite connectivity are two kind of independent, separate things. So whenever you try to use a satellite connection, you have to have a special satellite phone or satellite mobile terminal that talks with the satellite constellation. And also you might need to get the separate subscription. So Link is solving this issue. We are building a constellation of satellites that directly provide a cellular coverage to your phone in your pocket. So you don't have to use a different phone, like a different hardware, or you have to have a separate satellite subscription, but you can just keep using your phone. And as long as your phone is connected to a local terrestrial network, your phone will use that. But as soon as your cell phone loses connection from the terrestrial network, we will provide the connection as a roaming provider, so that cell phone can talk to our network, which gives you the cellular connectivity directly from space. So that's our solution. So here's a little bit about the high-level architecture of our system. So our Link satellite, each of our satellite operates as a network in a box. So this is different from a traditional bent pipe type satellite system, but our satellites are equipped with, for example, transceiver, as well as some of the components of a cellular stacks, cellular core network elements. And also, so on the payload link, we directly provide the 2G, GSM, 4G LTE, or 5G new radio interfaces directly to your phone from our satellites. Our satellites have inter-satellite links, so that we can, like satellites can exchange information, and also we utilize our ground station links to communicate with the existing terrestrial mobile network operators. So our network will operate like not only operate as a roaming network to your phone, but also like we operate as a roaming network to your the existing mobile network operators. And this way, we can achieve a really nice seamless connection with the existing networks. So SDR is our core technology to provide direct connectivity to your phone. So our satellite, each of our satellite is equipped with an SDR platform, which has an FPGA where we perform a fast and real-time signal processing. And that SDR platform is connected to our payload computer on satellite, where we run multiple cellular stacks, as I mentioned, GSM, LTE, and 5G stacks. And also we have implemented a special link DSP core, so we often call it a secret sauce, that compensates for for example, large Doppler shifts or time delay, so that traditional existing phones can directly talk with our phones. Our satellites. So Link is leveraging a really rapid do-learn loops for continuous development and testing, as well as deployment of this kind of technology. And SDR is actually a perfect solution, perfect technology to do this. So once we launch our satellite, as we all know, we won't be able to, we won't have physical access to our spacecraft. It's already launched. But the SDR allows us to update or upgrade the radio on orbit by simply uploading a new software or firmware, or it could be an FPGA image. So unlike the traditional hardware-based radio systems. So SDR is actually a perfect technology for satellite systems where we don't have a physical access. So here's a little bit about our current status. So we are currently in the process of rapid prototyping, as well as technology development, and we are also working on the on-orbit testing campaigns. And in a very near future, we will start an initial commercial service. So specifically, we are starting an initial commercial service in December 2022, later this year, which will give us intermittent connectivity worldwide. And in 2024, we will start a continuous commercial service that will give us a continuous, a truly ubiquitous wireless connectivity worldwide. Okay. So here's a little bit about past and future missions. So far we have launched 6 missions. So first 3 of them are hosted payload missions, and they were all completed. So first one was launched in December of 2018. And then the rest of the missions, Link 4, 5, 6, they are the free flyer missions, and they are currently on orbit. And the most recent one was the Link 6. So that was launched in April of 2022, so this year, with the SpaceX Transporter 4 mission. And we are actively testing our spacecraft with this spacecraft right now. And later this year, we are going to launch 3 more satellites. So they are named Link 7, 8, and 9. They are also free flyer missions. And we are currently in the final build phase of those spacecrafts. Of course, we are launching many more satellites in 2023. So let's see. So yes, I'm going to show some of pictures from previous missions. So this is the very first mission, Link 1, that was launched in December of 2018. This was, again, it was a hosted payload mission. So on the picture on the left, this was actually, I believe, everyone involved in developing the satellite. So it was a relatively small team, but we built a satellite spacecraft, and that was mounted on the nose of Cygnus. So as we can see on the picture on the right-hand side. The space testing was performed in February of 2019, and it was completed. Link 2 was launched in July of 2019. Team grew a little bit, and it was launched, and the testing was conducted from August 19th and 2019 to January 2020. Link 3. So this was launched in December of 2019. So the picture on the left is the one from, I believe that was before the handover of our spacecraft. This was also a hosted payload mission. Picture on the right, we can see our spacecraft with our logo in the middle with the two of us astronauts, Christina Koch and Jessica Muir. Link 4 that was launched in March of 2020. So this was our first free flyer mission. And the operation started in May of 2020, and it is currently on orbit. In Link 5, this is, we have a cool video clip here. So we can see our spacecraft was deployed in space along with several other spacecrafts here. So operation started in June of 2021. And the most recent spacecraft that was launched in April of 2022. So this is the picture from, I believe this was before the launch. So in the picture, we can see our spacecraft. This has actually, it has a shape of a pizza box. So if you look at the orange box, that's our spacecraft, and that's mounted. And this spacecraft is also called a Link Tower 1, and we are going to use this as our first commercial service spacecraft. Okay, so this is, here's some of the pictures of our facility. So we have a facility in Falls Church, Virginia, where we build and test our spacecraft. And also we have some of the equipment as well as FlatSat, that is basically a copy of the spacecraft that we have on orbit. So we can do various types of tests in the facility. And I thought it'll be cool to kind of include several pictures from field testing campaigns, previous campaigns. So we have folks who go to remote places where we have good overpass of our spacecraft. And also we have, there are places where, there are very little to no cellular coverage. So that's our target. So we go to multiple remote locations, including Falkland Islands, Canada, Bahamas, and also New Zealand. The picture on the bottom right is one of our setup here. So we can see antenna, and we usually use a spectrum analyzer to get some visual cue of what the downlink signal looks like. And we have some testing equipment as well as a standard commercial off-the-shelf phones for testing various services, for example, like cellular broadcasts and SMSs. All right, so this is my last slide. So we believe that everyone deserves a cell connection, cell coverage. So if you agree on this, and if you're interested in technology, including our SDR that we're using on spacecraft, please stop by. And also, we are hiring across disciplines, including electrical engineering, RF engineering, telecommunications engineering. So, and also we have a website there, so feel free to take a look. So yeah, I think that's all. Thank you so much.
Thank you, Tomo. That's awesome. That is awesome. That is like, especially how like, all parts of the world, like one place, like, in terms of isolation, another one that pops up and is in the neighborhood of Falklands is what is it, St. Helena, right? Like I think I saw like a documentary about it. But yeah, that's the thing. Like, it's really cool what you folks do.
Right. Thank you.
Awesome. So first of all, I'm going to ask if there's anyone from Analog Devices in the audience. Like if not, then we'll switch gears to MediaTek. So I guess I'm not sure. I think I see somebody going up and down from that's anonymous. So anyone from MediaTek who will be presenting at NEWSDR? MediaTek, anybody? I think let me check. Mike, do you know who's speaking from MediaTek?
Yeah, I think it's supposed to be. Let me check. Sorry, what was that? I made a switch at the end, but it should be Stan. Stan was indicated, but if not, maybe we can do questions for the other three speakers.
Yeah. Well, while we're waiting, also in case you're kind of trapped by multiple other avatars, which does happen from time to time, what's the phase cloak key, Mike?
If you hold G, you can walk through people.
Exactly. So if you're like completely stuck and it's like, oh my God, that's me, I need to go. Yeah, just press that and you should be all set. You should be able to phase cloak out of wherever you're stuck at. So, all right. So what we'll do is while we wait for a presenter from MediaTek, which again we're a little bit ahead of schedule. Are there any questions for our first three presentations from NI, Hayden, MathWorks, which is Mike, and Tomo from Link? So any questions? So again, if you have any questions, where the stage is to the left, there is a little microphone icon, and then there's a megaphone, like a green thing. And that is where you can ask your question and everybody's going to be here. So I think there is Bob McGuire. Hi, Bob. How's it going?
It's going well. So I had a question for Mike.
Yeah.
I am a big proponent of the Adobe Cloud license, which allows me to use all of their tools and update it constantly for a monthly subscription that's affordable. And so like a lot of university people and people that work with companies, when MATLAB license is purchased for me at the university or at the company, I am restricted in what I can do with it. So I would love to see MATLAB offer a subscription license of some type that's reasonably affordable by individuals. And if their experience is anything like Adobe, they're going to have a huge number of subscribers. Thank you.
Thank you, Bob. So Mike, and as well as Hayden and Tomo, in order to answer questions, you'll have to go back to the stage, to the little dot where you were presenting before, in order for everyone to hear your response. So just FYI. So otherwise, It'll be like, sort of thing. Okay, so Mike, take it away.
Okay. Yep, I'm there. So can you see and hear me? So just, Bob, just to make sure that I've got your question right, you're looking for MATLAB computational services on the cloud?
And yeah, Bob.
Oh, and so Bob has to come back to the circle too. There you go. Okay,
Yeah, I'm
You're good.
here now. Yeah. I'm sorry, Mike. What was your question?
So are you looking for MATLAB computational services on the cloud?
Yeah, no. What I'm looking for is a license with a monthly fee for your software, like Adobe does with their software. And so this allows
month to
individuals,
month.
yeah, month subscription. I mean, Adobe does this, and it's huge.
Okay, very interesting. So we don't have that license model right now, but we do have 3-month licenses. Would that work for you?
Oh, indeed. So look, what I'm trying to do is, you know how, look, I use every freaking toolbox. Who can afford that as an individual? So
right.
I would like something like the 3-month subscription, where if I'm not using a toolbox for a 3-month period, I don't need it, right? So I'll just, if this was something like this, and you could easily add and drop things as needed, I would do it in a heartbeat.
Yeah, probably. I mean, knowing from what our standard offerings are, the best that I can probably give you is that 3-month license. But honestly, I wasn't even aware of it until recently, and I'm thinking, oh wow, for a short-term project, that sounds simply delightful. So, but if you want to talk a little bit more offline, be happy to do it.
Mike, I'll call you.
All right.
I sent you a message. I sent you a message. If you will give me your contact info, I'll get out of the way and let somebody else ask. I see John Chapin's right behind me. I don't want to make John mad.
Okay, sounds great. Thank you, Bob.
Okay, thank you. So John, hi. Thank you for your question. Take it away.
Good morning. Can you hear me?
Yep.
Now, my question is for Tomo, actually, if he's available. Super interesting. It seems to me that with a 1 meter square antenna, you got to have a relatively big ground spot, which means there's going to be a lot of other folks transmitting in the same channel as that cell phone that you're trying to talk to. And that leads me to ask whether, going beyond secret sauce in the DSP, do you guys doing stuff with really much higher bit depth, much higher spurious-free dynamic range on your receiver to be able to close that link and pick out that particular weak cell phone transmission? It just seems like a really, really hard and interesting problem. Thanks.
Thank you, John.
Hi. Finally, I think my camera is working now. So thanks for the question. So yes, unfortunately, I cannot talk much detail about what we do. However, yes, we do have a kind of special secret sauce that handles a really weak signal. So we pick the signal, like really weak signal from the ground. So
but is that as much a hardware problem as a software problem? I don't know if you can answer that question or not.
So yes, so we are approaching from both. So we are actually improving our hardware. So I'm mainly working on the SDR, like software side, but there's a team of the hardware who's actually designing the antenna. So, and as well as some of the RF components. So there's one team who's dedicated to work on the improvement of increasing SNR, and also there we are making lots of improvement on the software side as well. So yeah,
cool.
I'm sorry. Yeah, we cannot. Yeah, I really wanted to talk more, but unfortunately,
Understood. It just seems like it's such an interesting and hard problem. So you guys have got to be pushing the state of the art. So thanks very much.
Thank you. By the way, thank you, John. I was part of the Spectrum Collaboration Challenge, so that's where I think we worked on. So I was part of it, BAM Wireless, if you remember.
Wonderful.
So,
thanks.
Yeah, thank you so much.
Thank you. So let's go back to
hi,
John. You have a question?
My question's for Hayden. I think I talked a little bit with him over Slack about this, but So one of the things that earlier USRPs have had the capability is the swappable daughter cards, and that adds a lot of capabilities for people who might have requirements that are different than other NI customers, and actually increases the base. And I think that's important. Lately, the USRPs have not had swappable daughter cards, and I think that. In the sense of as you go toward the future with the USRPs, you have the RFSoC interface, the RFSoC boards, which have large numbers of input channels. Are you thinking? Is NI's thinking in the way like, what if we use if we go back to a swappable daughter card architecture? I know there's a lot of engineering challenges, but is that something that NI is thinking about, and like the possibility of that happening,
Yeah, we didn't do that on the N320 and N321 radios, namely, because of you kind of highlighted the engineering challenges of like the interfaces were, I think, Neil, you probably can answer this better, but on the X310s, it was a little bit easier to support because the interface was a little slower speed. So, and one of the major differences between like EDIS, radios is we would sell them as, kind of kits where you could, modularly put it together. That's still supported on the N210s and the X310s, the various different daughter boards. We changed that interface pretty significantly with the X410. And as we went through like our characterization and validation, it became clear that it might be be a big challenge for like tech support and things of that nature, in that those interfaces were easy to break if you didn't, install them just right. And so it was kind of like that was sort of the decision, but we still did build the X410. You may be aware, or I don't know if you bought one and opened it up. It is a motherboard daughter board scenario. And we do like that architecture. We don't plan on doing it with like in as an open of a way on the X410 just because of that like tech support issue. But we are continuing to build newer daughter boards. We have I'm not supposed to announce new products in a big public forum, but we have one in the works that's kind of going to take more advantage of the as on the RFSoC chip. There's 8 channels in there. I think we're using the 8-channel variant, not the 16-channel variant of that chip. Mm-hmm. And we're only exposing 4 channels. And you're like, hey, where's my other 4 channels, right? We're working on another one that, challenge with doing that in a high frequency way is getting all those up converters and down converters and making it a nice, clean analog design in that space is pretty tough. But we are looking at it. We have a daughter board in the works that'll expose more of those channels, but will be more of a direct connect type of. I'm not sure the time frame of that, but it's that we are using the modular nature of the daughter board to be able to release products faster and sooner that meet some of these different needs. But no, we don't have any plans to open it up. Sorry to report, John. I know that's a key requirement for your applications. I know.
Well, yeah. Well, then it becomes down to because it becomes if you have sort of the open daughter board setup, you sort of don't have this fight with other between different customer bases. Like, oh, I need this frequency band versus this frequency band. If it's like, well, it's a daughter card. The daughter cards we're going to release in Q1 are going to have this frequency band, but here's like the Altium for making your own daughter card or whatever, daughter board. Then that makes it significantly easier for others who, if it's like, well, okay, like think about people like, Mike Rahim, who does visible light communication.
Right.
And I think the sort of open daughter board architecture allows for, I think, even more, kind of greater application spaces for these specific types of radios. And with the open software architecture that you have, I think it could create a lot of capabilities. So I'm sort of like saying there's I'm just trying to like kind of argue for there's a market for this. And I know it might not be as big as sort of 5G, but there could be some interesting things in these spaces that could work out. And there are people who, at Haystack, we have RF engineers who can set up like an take the Altium, design a daughter board, and then, as long as it fits in the right way, can be usable. And the other thing is, like, if you have NI then can take that. If it's like, oh, a lot of groups are using this daughter board, well, we can start producing them, and I don't know, maybe there's some licensing thing or open sourcing of it or something. I don't know.
Yeah, we've seen some of that, like on the N210s, like Mike uses on the on his Li-Fi stuff. That there's some third party companies that make their own daughter boards, and we've done that on some of our other like PXI products.
Mm-hmm.
But I think it's a fair point. I mean, for people that are looking at like frequency ranges that are not supported, like we have seen folks go way up into the millimeter wave. You and Mike are like down at the lower frequencies, on trying to get to those really, really low frequencies. So it's a fair point. I mean, we can talk offline, and I think you've connected with Philip and other folks, and we can get more detailed on kind of some of the roadmap plans.
Yeah.
Not in a public forum, but yeah, I think it's a really, it's a really nice thing of the X310s. One of the reasons we went away from it was so we can like assemble everything and test it, and it arrives to you like fully tested and functional. And so like there's those kind of like trade-offs of business and support. But I think it's good. It's good feedback, and we still like the modular nature of it. So.
Yeah. And
it's not like it's locked in forever, I guess.
As long as it's like just trying to get a feel for down the line, what's the feeling? And again, like you're saying that the sort of the options this is an open space still, and it's not closed off. And I think that's great.
Awesome.
Yeah.
Thank you, Hayden. Thank you, John.
Thank you.
So I'm just going to do another shout out, or do we have either Stan Kazov or Vince DeVecchio from MediaTek in the audience? Anywhere. Doesn't look like it. So actually, no. Sorry, I'm trying to scan through the folks. I'm not sure if Mike, if you see anybody, or John, anybody on the attendees roster. If not, or anyone from Analog Devices. So if not, any other questions for any of the three sponsors, from either MathWorks, Linked, or NI? Any cool questions or anything that? I think we do have somebody from MediaTek that's about to arrive. But Mike, you're actually on the Q&A square. You have a question?
Yeah, I was just going to tell you that Stan from MediaTek is here.
Okay, awesome.
He's having mic issues. Having mic issues.
Oh, and then I think Anton is also he's gonna take Stan's place. Awesome, thank you, Mike.
Okay,
thank you. No, that's awesome. Basically the usual from the last 2 years of video conferencing of the AV challenges. So I think while we're waiting for Anton to come up to the stage, and so are there any other questions for the three sponsors that have presented so far? All right. So if not, I think one thing to just to sort of recap while we're waiting for Anton to make it to the stage is that after the sponsor talks, we'll be having a sort of all 13 poster presenters give a 1 to 2 minute summary orally of about what their posters are about, and that's going to be followed by the networking session from 12:15 to 1:30 p.m. Okay. During 12:15 to 1:30 p.m., we will not be broadcasting via YouTube Live. There'll be kind of like a screen that's sort of like, hey, come back in at 1:30. And then what will happen is after that, we will have upcoming other SDR events and our 4 Rising Star presentations. And then afterwards, the technical sessions and the networking sessions, again, I think that's when the YouTube live stream will end. But Gather will not, and it will be hopefully quite active as we all engage with each other with all the topics that are happening this afternoon. So I believe Stan is on the stage. So Stan, you need to go onto the orange dot in order to be heard. Yep, there we go. So let's see if AV is working. Stan, can you hear me? Yep. So you have software mute off, and maybe check if you have hardware mute. Oh, there we go. We had something. Yeah, there we go.
I don't know. Can you hear me?
Yep. It's all good. Yes, Stan.
You can hear me?
Yes.
Oh wow.
Yep. Awesome. The technology works.
Well, it turns out my audio worked. I just didn't know how the podium system worked. So
well, welcome to NEWSDR, and thanks to MediaTek for the long term support of this event and supporting the SDR community. And the floor is yours. So take it away. Thank you.
Thank you. That was stressful. Okay. Hi everyone. Yeah, I'm Stan Klasov. I'm a compound engineering manager here at MediaTek. Today I'll give you an overview of what MediaTek does as a company, the type of work we do here in Woburn, Massachusetts, and how that all relates to software-defined radio. So what is MediaTek and what do we do? We're a fabulous semiconductor device company, and we develop chips for mobile, IoTs, embedded, computing, ASICs, smart home, and power. We're number one in market share in most of these and growing in others. And the majority of our revenue actually comes from mobile chipsets. In aggregate, we produce nearly 2 billion devices every year, and they go into products manufactured by these companies and others. We're present in some shape or form in every household, whether it's your Xbox, PS5, your Alexa, your wireless router. And in fact, we are we're number one in terms of Android usage in the US. On top of that, we're rapidly expanding. We've had a 50% year-over-year growth in the last 2 years. So we've been, relatively successful. I'd like to dive deeper into mobile chipsets. So what goes into a mobile SoC? So here's an overview of one of our flagship SoCs, the Dimensity 9000. It's a heterogeneous multi-core. It has an app processor, AI engine, GPU, and it also has an SDR modem. So these parts is what other teams work on in the company. And we here in Boston work on the SDR modem. And this modem is responsible for running software that drives the protocol stack for 3G, 4G, and 5G. So what's unique about the modem? It's a high volume product. There are billions of them out there. It's a deeply embedded proprietary DSP controller. It's very specialized because it has to run the single program it was designed to do, the wireless modem. The firmware that runs on it needs to meet the real-time constraints set forth in the protocol specs. It has to fit onto the chip, and it can't burn through all your power since it's in your pocket most of the time. So we focus on things that make the wireless firmware faster, smaller, and lower power. And that involves creating new instructions and operations in this processor, specialized memories and address generation units, special numeric systems. And whatever we do in all of this, it has to be easy to program because we have firmware engineers that use all of this. It has to be verifiable both in software and in hardware. And at the end of the day, it has to be manufacturable, testable, and delivered to our users. And we've put a lot of emphasis on making sure that all of this is as efficient as possible, since there are billions of these. So for every 100 million units that we ship, they cost in a ballpark of $20. So that's $2 billion.
That amounts to, I guess, a revenue of $5.5 million per day for each 100 million units that we deliver. And anything that can pull in the schedule to deliver this to the market faster, or reduce the cost, or increase the value, makes our team look a lot better. So we put a lot of emphasis on this. So what do we actually do in Woburn? So we developed the tool chain that drives this modem. So we work on the compiler, assembler, and the linker debugger that targets, again, the wireless modem. Our firmware engineers use a custom programming language and interfaces that we've designed to take full advantage of this processor. And secondly, we help drive the processor development. We don't actually do it here. And we go work with our users to make the whole ecosystem as efficient as it can be. And now I'll go over some of the projects that we undertake to give you a better idea. So I've mentioned that we put a lot of emphasis on area efficiency. So we're a compiler team, so we know how to do compiler optimizations. So it's common knowledge that large projects have code duplication, usage of things like C++ templates, inlining, and copy pasting can create cases where you have redundant and duplicated code in your executable. There are widely available techniques like identical code folding that can target some of these instances of duplication, but they cannot handle cases where differences exist. So if you have sequences of code which are largely similar, but have some differences, the technique fails. So we've had a project that identifies mostly similar sequences of code and folds them with appropriate fix-ups so that it works correctly for this case and that case, looking like this. So this helps us save an area, which means that the modem can be smaller, therefore cheaper. We also care about the memory footprint of our firmware, and we use inlining for performance, but inlining can actually increase or decrease stack usage, but on average, it tends to increase it. And traditional compilers don't really care about stack utilization, so they don't factor that into any of the heuristics. So here at MediaTek, we've improved the heuristics to factor in stack size into the inline decisions. And with that work, we demonstrated that we can get O3 level performance with Dash OS stack size. So we get the best of both. We also care about generating the most efficient instruction sequences possible. And we've had an intern project that took an existing off-the-shelf target-independent super optimizer, which takes short instruction sequences and turns them into shorter instruction sequences. We've demonstrated that we can do even better by creating target-specific hooks in that super optimizer and achieve even better instruction sequences. So that was presented at the LVM Dev meeting. So I guess going forward, we still care about improving the language that our users use to write software-defined algorithms for existing vertical stacks and anything that comes in the future. We care about understanding the performance profile of the firmware that runs on the modem and analyze it and find areas for improvement. Obviously, being a compiler team, we care about all the traditional performance and code size optimizations, ranging from generic that can benefit all targets to hardware-specific optimizations that only target our custom processor. We also are interested in defining what the next generation modem will look like. So what kind of ISA changes would benefit the latest and greatest standards? And since this is all custom, we need to make sure that it works and no off-the-shelf test suite would actually be useful here. So we're spending a good chunk of time synthesizing and improving randomized testing to create programs that simulate SDR firmware. So we have a lot of going on here. This is a rapidly growing area. Our products are used by billions of users. We have lots of new interesting problems and challenges to tackle. And we're also interested in having others join us. So if you yourself, or if you know anyone who are interested in this kind of work, please contact us, and we'll be happy to talk. That's it for me.
Thank you. Thank you, Stan. Thank you. So we do have time for questions, both for MediaTek, for Stan, as well as our previous sponsors. So any questions whatsoever from the audience regarding like any of the sponsor talks? None. Oh, here, Mike.
Well, I guess I have a quick question, not really related to me, but I know there's a lot of students in the audience, and Stan, to your last point there about career opportunities and things like that. I'm wondering if each of the sponsors could maybe spend 30 seconds or a minute just talking a little bit more depth about some of the positions we might have, might be interesting to some of the students out there.
Okay. All right. So I guess if there are no other questions, yeah. So I guess what we'll do is we'll take a 10-minute break while the students line up on like. So Mike, sorry. So where should the students be again? Should they be on the? They should be on the stage, right?
Yeah. Can you guys hear me? I don't know if you heard my.
Yeah.
Did you hear my question too, or was I muted when I asked the question?
No. I think. Can you repeat the question again?
Oh, sorry. Yeah, no. Maybe I might have been muted, but I was asking for the sponsors to Stan's last point there about career opportunities and such. I know there's a lot of students out here in the audience. If each of the sponsors can take 30 seconds or so to maybe talk about some of the career opportunities in a little more depth, I think that might be valuable to some of the people in the audience.
Okay. Actually, that's a great question. So Hayden, Mike, Tomo, and Stan, if you could please return to stage, and let's start with Mike. It seems like in the queue is then Hayden, Stan, and then Tomo. So Mike, take it away.
Sure. So we are regularly in a hiring mode for many different positions. We are investing among all of the different standards that we're building. We're investing the most effort in 5G, so there are opportunities there. But I think, speaking a little bit more broadly, one of the kind of unique things that we do at MathWorks is to bring in young engineers, often straight out of school, to serve as and be groomed for future opportunities, whether it's in engineering, development, marketing, documentation, customer experience. So that it's really kind of a, shall we say, a minor league where people's skills are increased, and then they get to choose what area in the company that they would like to migrate to. So there's always positions in that group that are available. So that's all I'll say for right now. But thanks. Great question, Mike.
Thank you, Mike. Hayden, how about yourself?
All right, can you hear me okay?
Yep.
Okay, I was trying to find it wouldn't unlock my camera. Yeah, I mean, we have a big R&D team, always, keep an eye on ni.com/careers. You'll, find some openings. We actually, one of the cool things about NI is we're a global company. Our SDR R&D team is actually split. It was originally out in California where Matt Edis started it in Santa Clara. We still maintain that office. We have an office in wonderful Austin, Texas, and one in Dresden, Germany, where folks do a lot in kind of like the 5G research space. So we occasionally have openings in these various teams. So if you're interested in working internationally, that's one other option. And also, I think talk to Neil Pandya. We do have some current openings in our technical support and kind of applications engineering space. So if you're passionate about open source SDR, and we believe Neil, even though he's anonymized on the pictures, we believe that he is not a bot. That I was trying to figure out. I was doing the Turing test on Neil earlier to make sure that he was actually human. I'm going to go with human. And if you love working with Neil, he's so passionate. Talk to Neil directly, and he can share some of the opportunities they have in his group in particular. And I promise he's human.
I think we need some sort of app out there that like, have you spotted Neil Pandya? And it's sort of like.
Yeah. Where's Neil? I think he's in Austin, Texas right now, but we can't be sure. All right, Stan.
Thank you, Hayden. Let me see. Stan, how about yourself?
Yep. Yes. So we are looking for a lot of things. We're looking for people who have experience in writing compilers and compiler optimizations. We're working on a full tool chain. So we're also interested in assembler experience, linker experience, debugger, and also interested in people who do language design and have broad experience in writing SDR algorithms and optimizing those algorithms to fit the constraints. We offer both full-time positions and internships. And if you saw anything in my presentation that slightly interests you, then we'll probably have a position for that as well. So I listed my email. Ping me on here if you know anybody who would be interested in helping us.
Awesome. Thank you, Stan. Thank you. And Tomo.
Hi, can you all hear me?
Yep.
Cool. Yep. So Link also has various openings. So and especially we like young engineers. So we have positions like SDR engineer. So it's like me, or we have a modem engineer. So those are heavily focused on like a DSP and algorithm designs. We have RF and electrical engineer positions. So those are a little bit more towards the analog circuit design and RF circuit designs. And also we have a bunch of other positions, including some of the mechanical engineers, spacecraft communication engineers. And also, of course, we have some like senior position openings as well. And also we do internship every year. So if anyone's interested, we have a website, so feel free to contact us. So,
perfect.
Thanks.
Perfect. Thank you. So with that, let's first of all thank all our sponsors again for the great presentations, as well again of the support of this event and and making it a reality. So let's applause, or if you got the icons, like I think there's like bouquets and stuff, and thank you. So now, and it seems that it's also possible to make your avatar dance too. I did not know that's possible. Anywho, so what we're going to do next is we're actually going to call all 13 presenters to come on down to the stage to line up and kind of give your 1 to 2 minute pitch about your about what you're doing for your poster, which is the session right after. So may I ask like all 13 folks to come down? So let me see. I think I have the latest. All right. So so in terms of order, I think Mike sent the list. So I'll give 1 minute for everybody to come down to up on the stage.
So I have all of the elevator pitch slides, so it might be easier. I can share the screen, and as you guys all come up to the podium to give your elevator pitch, you can just talk directly to it.
So maybe the first one's Rigel. Is Rigel in the audience? Yay, Rigel. So like I think Mike, do you have? There we go. And
hello.
Let's see. Your camera is still either initializing or. Oh, there we go.
There we go.
Probably like the coffee cup is blocking it or something.
There we go. Okay. Good enough.
Well, welcome, Rigel.
Quick pitch. So, my name is Roger Capello. I'm a postdoc here at MIT Haystack Observatory in Westford, Massachusetts. This poster is about a program that was started almost 30 years ago, a brainchild of Alan Rogers and Erwin Shapiro, actually. And the idea is just to have, for educational purposes, to have a small radio telescope made out of easy parts that anybody can go buy, any institution or personal person, and then be able to make their own observations and be part of a larger community that own a bunch of these. There are already a whole bunch of them out there in the world. It's sort of declined a little bit, but then about a decade ago, some of my colleagues started getting back into it and getting it resurrected, especially with the great progress that was made with the software-defined radio. They were able to use that, and now it's getting to a point where it's nice and usable again. Has a nice interface online, and anybody can basically, any institution can create one of these on their own and build it, and then use our software to make observations. And I'd be happy to talk about it more with anybody that shows up at the poster.
Awesome. Thank you, Rigel. So what we're going to do again is we won't have any Q&A here. We're going to go through every 1 to 2 minutes. And then from then on there, we'll just go into the poster session right after these elevator pitches. So next up is Ka-Kit Wong from Haystack Observatory. Ka-Kit, are you in the audience? There we go. Yep, I see you. Yay. Yeah, so you're going to need to go into the orange spot. Yep.
Okay.
Yeah, we can hear you. We can hear you. So you're all set. Take it away.
Okay. Yeah, so I'm Ka-Kit Wong, and I'm an undergraduate at Boston University. And so for my senior design project, I've been working on this RF monitoring project, and essentially I just used our RF sock, like the Xilinx RF sock 2x2, to create, to collect data and collect RF data and process data, which will be displayed on a web application. The goal for our project is essentially be able to visualize data and help essentially it's like to visualize data better, and the purpose is due to the fact that the RF spectrum is becoming increasingly congested. So we thought it'd be good to have some sort of tool to be able to visualize and understand the data for research purposes. That's it.
Thank you, Ka-Kit. Thank you very much. Thank you. Next up is Yiyu Zhang from Northeastern University. And you are mute, I think. Like, or gather mute. Yep, I think I don't. Audio check. Can you hear?
Hi, hello. How are you?
Good. How are you?
Hello, everyone. So today I want to present an intelligent sample selection method for reducing the training time of neural network for DPD. So DPD means the digital predistortion is used to linearize the power amplifier's nonlinear behavior. So when neural network was used in indirect learning or direct learning architecture for DPD, we really want to accelerate the training phase. Besides besides improving the speed of matrix solving for backpropagation, we could also reduce the training sample size. But how to select those samples to keep the same accuracy performance? Usually, the convolutional neural network will add extra layers to extract some features to reduce the training sample size for the neural network. While that will cost a lot of hardware utilization and increase the complexity. So we propose probability density function-based subsampling methods. By binning the outputs of PA by their power levels, we can put a threshold like the red line showing in the figure, the histogram figure. So we can separate the linear part and nonlinear part of the output. Then we can keep a low fraction of linear samples while keeping all nonlinear samples to train the neural network. So the neural network can be really focusing on modeling the nonlinear part instead of being trained with a lot of similar linear samples. From the experiments based on Xilinx RFSoC, we found that this method can give us similar accuracy of around minus 26 dB for DPD compared with using the whole dataset DPD. And this method can accelerate the training speed by many times, which is showing in the result figures. And more details will be shown in the poster session. Thank you.
Fantastic. Thank you, EU.
Thanks.
Xiaoyang Han from Northeastern University. Come on down. Oh, EU, you might need to move from the spot. EU? Ah, perfect. Thank you. Yay. Okay.
Hi, so I'm Han, also from the Northeastern University, even the same lab from EU. And here, I like as this, I'm also, sorry, my slides goes off.
My fault. I'll put that on 1 second. Sorry. Just
Okay.
closed the wrong window. Oops. All right, here we go.
Yeah. So as described my described by my colleague EU said, like digital distortion is very important in current modern communication system, and we would like to achieve the several goals like linearize the power amplifier and achieve the power efficiency and the adaptivity. Specifically for adaptivity here, we mean like we would like to coordinate our system to coordinate with different bandwidths, with different frequency and different modulation schemes. Hence, we provide this real-time DPD system. It allows us to like work with these different kind of modulation schemes or different bandwidths, and it can adaptively change through the time. And this is achieved using the Xilinx RFSoC. It's an ARM FPGA heterogeneous platform with the help of MathWorks SoC block set. It's a very genius product, and we carefully partition the system among the platform, and we manage the data transfer between the boundaries, and we have our test set up on the right hand side. And similarly, we can achieve the similar result as the traditional DPD, and also the from the theoretical theory and or Simulink or some result from that. And if you want to know the details about it, please come to my poster session. And that's it. Thank you.
Awesome. Next is Hamza Ali from UMass Boston. Come on down, Hamza.
That's actually one of my students. I know he had a conflict until 11:30, so we might. You mind if we hold off on that one till the end and skip over it for now?
Okay. How about Evan Urban? Hey, there we go, Evan. Also from UMass Boston. And you're on mute. Software mute. Still on mute. Let's see if I can unmute you. Bloop. No. Evan, can you hear us? We can't hear you.
I think there we go.
Sort of. It's doing a funny mute icon. Evan, can you hear us? I think you're talking. I think you're talking, but we can't hear you.
I can hear over here. I don't know if it maybe.
There we go.
Seems like.
Can you hear me now?
Yep, we can hear you now. Take it
All
away.
right. So I'm Evan Urban, speaking on behalf of UMass Boston project, and so we had used SDR for WDMA testbed for researchers. So what WDMA is wavelength division multiple access. So we're able to transmit multiple signals and receive them via multiple receivers. So the diagram on the right, we're receiving 3 different color electrical signals, which is converted by our transmitter into a optical white light. And then we have 3 photo receivers, each with a different optical color filter. And so we're able to receive individually specified signal. Our testbed design consisted of a steerable RGB LED transmitter, which our group created ourselves. We had used multiple photo receivers, each with different optical filters in order to isolate the signal. And we had used GNU radio and USRPs for signal conversion and also signal generation. In the USRP, we had used a X series USRP for our transmitter, and because this is an optical system, we were able to use all 4 outputs of the USRPs, including the imaginary components. And then we used the N series USRPs for the receivers, which would just be one USRP for a receiver. And then so GNU radio, the diagram on the right is our transmitter flow chart. And so what we were able to do is we were able to combine 2 signal sources, and then we were able to use a variable which we could switch from 1 to 0 to alternate our color of transmission from either blue to red. So for a demo that we had performed was we initially would transmit a signal through the blue channel and receive it through our blue filtered photo receiver. We then introduce a interference signal at a different frequency. In order to eliminate this interference, we then switch the variable on our transmitter to the red channel and switched our receiver to the red channel as well to be able to eliminate that interference and still receive the desired signal. And so our project was able to provide researchers with the ability to investigate further wavelength division multiplexing and wavelength division multiple access.
Cool. Well, thank you. Next up is Charles Monte from UMass Dartmouth. I think, what's the mascot? The Corsairs? So take it away, Charles. And I think you're on mute as well. Yep, there we go.
Is the microphone working?
Yep, now it's working. Let's rock and roll.
Okay, so I'm doing the minimally constrained neural architecture search in convolutional neural networks using genetic algorithm for modulation classification. So the main goals of this were to create a convolutional neural network from no initial network and no previous assumptions on the data set, and just allow genetic algorithms to automatically figure out a good network for this data set. So the only constraint is that it can train, and it has a fast runtime and just an hour or 2. It has the freedom to use layers and parameters anywhere separately, so there's no constraints. And that there's also skip connections or possibility between any of the layers. The application being tested on modulation classification data sets, like the DeepSig benchmark data sets. So on the right, is just a process overview where the only input needed is the data set. The generation is created. Constraints are tested on the networks that are proposed by GA. And if they pass, then they're trained. If they fulfill the requirements, such as a goal accuracy, then that's the output and it ends. On the bottom is just how the problem is communicated to the genetic algorithm, where the layers are encoded in binary variables. And a 1 is that GA says to allocate that layer, and a 0 is to not allocate that layer, and the networks can be created from that. So for any more information, it's poster 7.
Awesome. Thank you. Thank you, Charles. Next is Todd Morehouse, also from UMass D.
Hello, everyone. My name is Todd Morehouse. I'm a PhD student at UMass Dartmouth. I'm just waiting on the slides. Everyone can hear me, right? Awesome. Thank you. So our research is on spectrum sensing in a cluttered RF environment using faster region-based CNNs, or FRCNN. FRCNN is a augmentation on regular convolutional neural networks that basically allow it to do object detection. Normally, a CNN can only detect if a single object is present, such as, say, a signal is present somewhere in this band. But if there's multiple signals present, it's not able to tell you the location of each and every one of them. So our goal was to use FRCNN, which has that capability to do this. There's been implementations of this before, but they required you to first take the received IQ samples and convert them to something like a spectrogram, because FRCNN was designed for image processing, and it wasn't able to work on 1D signals. Our goal was to modify this so that we can process these 1D signals. So the first figure here just shows like our modification to this. We mostly modified the region proposal network, the region pooling, and box regression layers. We then tested this with some synthesized samples and over-the-air samples, and we found that our architecture was able to find signals at a higher accuracy than the spectrogram case. And we also tested this using SDR. On the rightmost is some of our results using the SDR over the air in real time. We also augmented this with modulation classification to show the ability to extract each signal that we detect. So every signal that's detected is isolated and then passed through another CNN to be classified by its modulation type. So I'd appreciate if you check out our poster. I'd be happy to answer any questions. Thank you.
Awesome. Thank you, Todd. Next up is Michael Kuhanjian. Michael, come on down from Fresno State, which is also, if we count back, like, that's 3 hours behind us. That's, a little bit early, if not there. Next is Hovans Kulhanjian, Fresno State. Or
I talked to the Fresno State folks about half an hour ago, and I thought they were here, but
okay.
I'm not sure if I see Hovannes. No.
Hovannes, Michelle. Like we could skip the Fresno State folks and then circle back at the end to actually, is Hamza in the house?
He's not. I guess not yet. If he's not here, I can present his afterwards too. But okay. Do you want to do the last two? Oh, here comes Michelle now, I think.
Oh, Michelle.
Maybe. If you're out there in the audience, Michelle, you can come up to the podium to present and stand on the orange spot.
Yeah, you have to go in the orange spot right in the middle of the stage. Yep, there's some steps. Circle around. Yep, there we go.
Yeah.
Yep. Now
Can
we
you
can
hear?
hear you.
Can you hear me? Okay. So yeah, I can do the RF fingerprinting.
Okay, you should be good.
Okay, thank you. Yeah, so this is the project we did with the collaboration with the Boston University and Fresno and the University of Ottawa. So basically, this is we used based on deep learnings such as CNN network and all. We try to identify transmitters such as Pluto and other USRPs using deep learning techniques to classify, which is called RF fingerprinting. And also we use some signal processing techniques as well, such as we did spectrograms and stuff like that. And based on that, we fitted the CNN network and to identify the different transmitters. And we actually have very good results obtained through this network and what we learned. For example, if you're only using Adam Pluto or just one type of USRP, then we had 99% accuracy results and so on. And we are able to get very good results with this type of network. So yeah, this was our project, and so this is we'll be continuing on doing more studies to improve the accuracy result, and then more detailed, I think, will be I can discuss during the workshop. Thank you.
Awesome. And then Hovannes Kulhanjian from Fresno State. He has two other posters. I'm not sure if Hovannes is in the audience.
Yes, he's in audience, but I think he doesn't know that he has to come up here.
Oh, okay. Hovannes, thank you, Michelle. Hovannes, come on down to the stage if in order to present. No one can hear unless you're on the orange spot. Hovannes. Okay, so while we're waiting for Hovannes, maybe Hamza, you're in the audience. So how about you want to come up and present your 2-minute elevator pitch? Hamza? Yep, there you go. So you have to go up to the stairs and nope. Oh, yeah, you can do that. Okay, there we go. So Hamza Ali from UMass Boston, take it away.
All right, give me 1 second. Let me just put this on present. All right, share screen.
Awesome.
All right, so basically, just to start off, throughout the years, we've seen an introduction of many different wireless devices, and these devices have many different capabilities. And in the beginning, they had very basic capabilities like device applications such as email and SMS, which creates a demand for network capacity. And over the years, researchers have found ways to improve network capacity and to increase it, which has allowed more devices to be able to utilize more advanced applications. So throughout the years, we've seen even more advanced like smartphones and introduction of VR headsets. And this has allowed us to have device application capabilities such as live streaming, virtual reality, even the meta world that's came out recently, which has all contributed to this demand for more network capacity. And basically the goal for this project is to create a research tool for a testbed that emulates an ultra-dense wireless environment. And what it will do is it will assist researchers in determining ways and techniques to be able to improve network performance with the use of a software-defined radio. And yeah, that's a basic overview of what I have.
Thanks, Hamza. Thank you so much.
Yep.
Okay. And now Hovannes, are you in the audience? Well, I think Hovannes, I think you are, but you'll need to come up in order to present your two posters. if not, we'll just switch gears to Yael Rogoshinsky. Yael, come on down.
Hello?
Yep, I can hear you.
Okay. Hi, I'm Yael Rogoshinsky from WPI, and over the past pandemic, a lot of people started working from home, and one thing that people started realizing is the broadband in this country is not up to par, which is defined by FCC's definition of people needing to have 25 megabits per second as their data rate. And what we also saw is that the infrastructure is just not there. So to ensure that rural areas specifically have the data rates that the FCC has defined as the minimum level, we want to find a cost-effective manner so that more people are able to get this type of service. So our proposed, or at least my master's thesis, the proposed approach for my master's thesis is a millimeter wave backhaul network with large amounts of last mile technologies, which we are using LTEU. So I will just be presenting the work that I've done so far.
Awesome. Thank you, Yael. Thank you. Maybe to keep thematically, how about we call Joe Murphy up to the podium, and then we'll swing back to Havanas.
Hi, can you hear me?
Yep. And
Yep.
the server in the back.
Yes. Yeah, so hi everyone. I'm Joe Murphy. I'm a master's student with background noise.
Oh no, you're fine. We can hear you.
Am I good?
Yep,
Okay.
You're golden.
Yeah, so I'm Joe Murphy, master's student at WPI, and I actually work with Yael and Professor Wiglinski here on some work. And so kind of to follow up on that idea of there not being, enough bandwidth and kind of, a lot of people in America not having adequate internet available to them, I'm taking a bit of a different approach because obviously deploying infrastructure, it's expensive and it takes a while. So I'm looking at creating a system that we're calling our intelligent router, where we take the limited bandwidth that we have available and we create a system that can efficiently and effectively maximize that bandwidth by dynamically allocating how much bandwidth each host gets. And so we're doing this with a bit of a two-part algorithm that will actively look at the network to determine how much bandwidth is required for each individual host, and then allocate as much as possible to kind of try to maximize everyone's needs fairly and effectively. And so currently we are doing a lot of this testing in emulation and software, but we do also have a test bed that's in construction out in Missouri that you can see here on the right that we're going to be deploying this to. And I'll go a lot more into detail with a lot of that later in the poster talk. So thank you all for coming, and I hope to see you at the poster.
Thank you, Joe. Thank you so much. So now let's go back to Havanas. You have to go on the orange spot. Yep, almost. Yeah, yay! There we go. Awesome.
Hi everyone. Let me see if I can. How can I go and the presentation? Okay. So here, what we're doing is we're doing multi-user visible light communication using software-defined radios. And this was in collaboration with Michael Rahim from UMass Boston. And so what we were doing here is we were transmitting information using visible light communication. So the key principle behind visible light communication is that unlike in RF, where you can do, for example, QPSK, transmit imaginary components, in visible light communication, you cannot do that because you have only ones and zeros. So in order to tweak that, there is an interesting principle called Hermitian symmetry. So what we do is we take the imaginary components and then we use the principle of Hermitian symmetry, and then we use that as a secondary data that you can transmit. And then at the receiver side, we go back and reverse that and then get the information bits. So we have built software-defined radio flow charts and even written Python codes for the Hermitian symmetry. And it's an open software-based Michael Rahim has developed previously with his students. We were working in collaboration with him. And so we have also presented this work to AFRL SDR challenge workshop that we attended in April. And so we got really good results. So we could transmit simultaneously for multiple users, let's say data, audio, voice, and so forth in the same using different types of channels. So yeah, that's about it. Thank you very much.
Thank you so much. Thank you. So if this doesn't get everybody excited, I don't know what will. So, I mean, in terms of all these great presentations, all these posters, so that concludes kind of like this sort of 1 to 2 minute elevator pitches of the poster presenters. So we're going to now switch gears into the actual networking session. We're a little bit ahead of schedule. Theoretically, we're supposed to start at 12:15. It is 12 on the dot right now. So that's good. That just gives more time for us to all network. So we'll reconvene here at 1:30 p.m. Eastern time. But in the meantime, check out our sponsors and exhibitor tables in the, I don't think it's here. It's actually in the exhibitor hall, the sponsor hall, as well as the posters. And perfect. Thank you, Mike. Because so basically just head south from this room, and there should be lots and lots of doors, and we should be sort of emptying out into that space, and that's where you'll be able to engage with everybody. So there's also, if you check it out, the poster presentations are, if you go down and then make a left, there should be a door. And if you enter that door, that's where the posters will be. The exhibitor tables and such, that's of course center stage over here. There's also the 2 breakout rooms that we'll be having this afternoon for the 2 breakout sessions, right? We have a lounge area, like, yeah, we do have a lounge area. And then there's other sort of rooms that you can go to if you want to attend any of like the sponsor breakout talks and such. And private spaces are pretty cool because that will enable you to have one-on-one communications without you hearing people surrounding you because they're in earshot, and vice versa, them talking to you. It's kind of like where I am right now on next to the stage. I can't hear anybody that's surrounding me. There's a lot of these kind of like restricted spaces where if 2 people or 3 people are in that grayed out zone, you won't hear anybody and they won't hear you, even though they're physically next to you in virtual space. So with that, I guess I'll see you all at 1:30. For those people that are like following us in YouTube Live, I'm going to disconnect I'm not going to disconnect the YouTube Live, but I'm just going to put sort of like the NEWSDR 2022 cover slide, but not really broadcast anything from the gather space until 1:30 when we're back in the main auditorium. Okay, so 1:30 we'll resume the active presentation program where we're going to have, you know, first of all, the sort of upcoming SDR events, followed by the 4 Rising Star presentations. And then after that, the breakout sessions, well, that's not going to be over YouTube Live. The YouTube live stream will end then, and it'll be only gathered. So with that, looking forward to seeing everybody back at 1:30. Mike, I'm not sure if you have any
Just a quick note also down here in the bottom left, there's a couple of sponsor breakout session rooms. I know MathWorks and I believe NI have a little bit of a technical breakout session. So if you're there around 12:30 to 1 o'clock or 1 to 1:30, stop in there. You can hear a little more detail about some of the stuff that they're working on in depth based on extending what they talked about in their the quick pitches from earlier today.
Awesome. Thank you. Thank you, everyone. So see you at 1:30.
Alex, just a heads up that you're still broadcasting to the room. You're still on the spot, so you're still just your video is still broadcasting, not your screen. Just you and your audio. Okay. Just letting you know. Yeah.
Hey.
Hey, Alex.
So we're back at 1:30 in the main room, and then we've got the networking session, lunch and networking sessions and all that.
Yeah, so just networking here. Yeah, we didn't really post anything too much for the industry breakout sessions. I just got a quick blurb from Mike. I'm going to put that up by his room so that people can know what he's doing. So let me go ahead and do that before I forget.
Sure. For the plug that we're doing for GNU Radio Conference and stuff like that that's kind of just a quick, like a 5-minute spiel. I assume it's a.
Yeah. Just information about when it is, what if people can submit posters or whatever kind of stuff you want to talk about, or papers. I don't know what the process is. But.
Okay, and for the AFRL Beyond 5G Challenge, who's speaking to them? Yeah. Yep, I'm here. Okay. Okay.
And turn on unmute. All right, so just a thumbs up. Can folks hear me? Yay! Okay, awesome sauce. And let's see if YouTube broadcasts me. So if you hear this like weird audio echo thingamajiggy, my apologies. Like I have like this, like the YouTube live link on the side here. And perfect. All right. So just want to welcome you all again to the afternoon part of NEWSDR 2022. So what we're going to do is we haven't done this before, but we've seen this done in other conferences where folks who are part of like kind of the same sort of technical community, but are organizing relevant events. So let's say here's one conference, but there are 2 other or 3 other conferences or activities or workshops that are kind of within the same theme that might be of interest to the attendees. Kind of do kind of a quick pitch for what they're doing, just to kind of get on everyone else's radar. And this way, there's kind of this like positive feedback loop in terms of like growing interest, growing the community, sort of like really an interchange of like of ideas and people getting more engaged. So what we're going to do is we're going to first of all cover two of these types of upcoming activities. One, it's going to be the next iteration of the Air Force Research Lab Beyond 5G Software Defined Radio Challenge, and we're honored to have with us here today Steve Harry. And then afterwards, we'll talk about GRCon, or GNU Radio Conference 2022, and we'll have Neil Pandya give a quick presentation about that as well. So with that, Steve, if you're in the audience, or actually Brandon, yep, Brandon, if the orange spot marks the spot. So let's see. So audio, awesome. Can you say audio check? Can you hear me?
Yes, I can hear you. Okay. Can you guys hear me?
Yep. And audience, can you hear Brandon?
I think I see 1 thumbs up. Yep. There's a couple thumbs up.
And a radioactive signal. So
yeah.
I think we should run. All right.
Great.
So if you got any slides, I think I'm not sure if you know how to share slides.
Yes, I'm going to push the slides here.
Awesome.
Let me know if you guys can see them here.
Definitely. So
all right.
take it away. Thank you.
All right. Well, thank you. And thank you for having us here. My name is Brandon Matthew. I'm here. I work at the Air Force Research Lab in Dayton, Ohio. Sensors Directorate. We are here. I'm here with Dr. Steve Harry, who is my colleague and co-organizer of this challenge. This is we're kicking off our 5th year of this challenge, and a lot of you have either participated or at least heard of the challenge before. I saw in the poster session, 3 of the posters were actually from the challenge this past year we held over the 2021 to 2022 academic year. This is a university challenge, and I don't think I have to tell anyone here why SDRs are cool or why we use them, or all their capability or anything like that. But for our challenge, what we're trying to do is encourage universities to incorporate them into their curriculum and produce more students and capability from a skill level for the workforce, and specifically for defense needs. SDRs, their capabilities and speed is very important, and we need more people. We have the hardware, we have cool technology. We just need more people to actually utilize them and understand them. So we've designed this university challenge to incorporate that and try to promote teams to start working with them as early as undergrad level. This is really targeted for like senior design, undergrad senior design level / kind of like a master's project. But we've had PhD students partially work on this. We've had postdocs and young professors lead or mentor groups, and we like having that range of skills. Even having undergraduate students working with the radios or various different hardware. So some details of it. This year, the 2022 to 2023 academic year, we are working on the call currently. It'll be very similar to the previous years for teams and people who are somewhat familiar with it, but it runs the full academic year. So we'll have a call out for proposals over the summer and into the early part of the fall semester. So we try to target September for a submission date. Our teams, it's very open. There is no specific challenge. This was kind of created from a Hackfest idea, but the RF spectrum and these radios are a little more complicated than a weekend or a week or a certain time period allows. So that's where we've expanded it out to like a full academic year, and we don't limit you in terms of any specific challenge or goal. It really, what do you want to do with the radios, and what can benefit your community or your research work, and trying to support that. Primarily, our support is through awarding hardware. We provide kits that include 2 SDRs. These are the B210s from NI and NETIS, along with a couple multi-band antennas just as a basic kit. We ask that teams provide their own laptops and software, and we're open to any software that you want to use. You want to use GNU Radio, you want to use LabVIEW, you want to use MathWorks, you want to write your own C code. We're open and have no limitations there. So we run this over the course of the school year. Usually this year we asked for a mid-year report before the winter break. And then we try to engage with teams at least a couple times virtually, make sure they're on the right track, make sure we answer any questions that you have, and try to provide as much guidance to get the most that the students and professors can out of interacting with Air4L, and we're trying to incorporate more interaction from industry this year. So this past year we had representatives from NI, specifically Hayden Nelson was very involved with the support and judging this year. Neil Pandea was involved with doing some onboarding presentations at the beginning of this past year's competition. So that was, I believe, like October timeframe, October, November. And then we've also had representatives from Collins Aerospace and MathWorks also join us in terms of judging and evaluating the teams. So we're trying to up that and get more and more involved industry there as well. So once we get through the school year, we do a finals where this past year we had 17 teams, and I'll view those here. Here are the 17 teams that we had this past year. You can see a lot from the New England area, a lot of teams represented here in the conference today. Also a lot of local to Dayton area and Ohio regional teams, but we've had teams. We actually went international this year with teams for participation from the University of Ottawa, and we're open to that. But we're open to teams collaborating. As you can see there, multiple teams were across multiple universities. So out of the 17 teams, we invited 10 of them to Dayton for a finals this past April. We're planning to follow that, kind of continue on that this year, have a finals in April 2023 where we pay for travel costs for 2 students and 1 faculty to come. We down select, or we're hoping to have to down select if we have a good turnout on proposals and team participation, down to about 10 to a dozen teams, just for logistical reasons. We only have a certain amount of limited space, and bringing them here for an in-person demo and interaction with the other teams. We also have travel grants that are available for any participants and whose research was involved in the SDR challenge. We have a call for individual student travel grants to go to a conference to pay for travel, to reimburse for travel and conference costs for you to submit that, get your paper accepted, and present at those conferences. So like I said, we don't limit who and what. You can see there's a lot of different types here, some hardware, a lot of there's some AI code, development and utilization. There was, using the radios with the optical data communication. So, some hardware interaction. We like to see that. I'm a hardware guy myself, so I like to see using SDRs not as just an SDR like it came in the box. If you crack it open and use it, I definitely give you're getting some brownie points from me on that sense. We did some, more traditional where you do some, direction finding or direction of arrival kind of stuff. We're open to really anything, and we like when you can contribute back to a larger effort, including professors' research and or open source work. You can see there the out of tree module for GNU Radio, the Rutgers this past year. I believe they are reutilizing that and potentially making that OOT for public release on GitHub. So we're encouraging that and want to see teams do more of that kind of work. This past year, like I said, we had a in-person demonstration and competition between the top teams. You can see there in the middle a lot of familiar faces. We had the WPI team, 5G user equipment selective jammer was our top seed in the unconstrained group. And then the University of Houston implementation of deep learning radio and signal classifiers there on the right team was our top out of the constrained category. So we had 4 teams in each category that were ended up invited and participated. And there's all our participants there in the middle. So, and like I said, this is more for everyone's awareness. We are accepting proposals for next year's challenge. There's our link and a couple emails, including Tony Liza, which is our collaborator at WBI. They help us coordinate and run this every year. They're a local company here that supports AFRL. And then Steve Harry, my colleague, who also is kind of got this off the ground and has been the lead organizer in this for the past 5 years. So if anybody has any questions, I'd be happy to take them, and or I'll be floating around the conference here for a little bit longer. So.
Okay, great. So I'm not sure if perhaps we have a short presentation for a GNU Radio conference, and then maybe we'll take 1 or 2 questions if there are any from the audience. But thank you, Brandon.
Yeah, thank you, everybody.
Thank you. So Neil Pandia from GNU Radio Conference 2022, come on down. There we go.
Hello, everybody. Can you hear me?
Yep.
Okay, thank you. I just wanted to say a few words and promote the GNU Radio Conference. This will be the 12th year that the conference is running, so it's also been running a long time, just like NEWSDR. This year, the conference will be on September 26th, so the last week of September. It's usually always run in September. I think we've only deviated that once or twice. And this year, it's a little bit later. It's not in the middle of September. It's the last week of September. The conference is a week long, and it's kind of the primary conference or user event for the GNU Radio project overall. And it's had a good turnout over the years. We have about 350 people. We were virtual for 2 years, but last year we were physical in Charlotte, North Carolina. This year we'll be physical in Washington, D.C. At the Hilton Hotel there. I'll put the website in the chat in just a minute, and you can get more information about the event. Even if you can't make it for the full week, there's still value in coming for a part of the week. Most of the technical presentations are in the middle on that Tuesday, Wednesday, Thursday. So even if you came just for that middle part of the first half of the week, that still is probably useful. A lot of people come to GRCon. If you're not familiar, it's as I said, the primary conference for the GNU Radio project and the GNU Radio software. So a lot of the people that author a lot of the tools or out of tree modules and the core developers and the whole user community come, and it's a great way to meet people face to face. If you're looking for new ideas or brainstorming technical topics or technical projects, or really anything, even looking for a job or even looking for new tools and other things that, for a particular project that you're working on, you might not be aware of what's out there in the community. It's a great way to find out who's working on what. The people who come are pretty well distributed between industry, academia, and government, and the hobbyist community. So it's a mix of all kinds of different people. Right now, the call for papers and basically abstract submissions, posters, and sponsorship opportunities is open. The call for participation is going to end at the end of the month. So there's still a few weeks to get something submitted. Just an abstract is all that's needed. The actual paper doesn't have to be submitted until a couple of days before the conference, in fact, so plenty of time, something like 4 months still. If you have any questions about any aspect of GNU Radio Conference, please feel free to reach out to me. I'll put my email in the chat as well. Any question along the lines of sponsorship or abstracts or even attendance or anything like that, I can help answer. So with that, I'll end there, and I hope to see you all in Washington this fall.
Awesome. Thank you, Neil. Thank you. So maybe if there's a couple of minutes for questions, are any questions for either Neil or Brandon about either of these upcoming events? Like, does it use Gather? Just kidding. No. Any questions? Okay. So hearing none. Brandon and Neil, thank you again so much for sharing with us these upcoming events. Very, very excited to see more opportunities for people from the software-defined radio community to reach out and connect with other members and really kind of like, sort of exchanging those great ideas and forming new collaborations. So with that, now it's the exciting part. Well, everything's exciting, but this is the first time we've done something like this. The Rising Star presentations, like we've been like over the last several years, we've been talking about opportunities to see like how about like folks who are up and coming in the sort of the wireless, the software-defined radio, the IoT, the cognitive radio, like essentially the people who we see will be like the sort of like the innovators and leaders of our community. And so for this year, we have 4 excellent presenters who will each be giving 15 minutes of like, kind of like a sort of overview of what they've been doing as part of their research or activities to kind of really, and again, enable more of that connectivity with the rest of the community. So among them are Dr. Maria Zaleva from University of Albany, MIT Haystack Observatory researcher Ryan Voles, Dr. Nathaniel Frizzle from the University of Scranton, and Dr. Basima Islam from WPI. So first up we have is Professor Zaleva from the University of Albany. So yeah, Maria, like where Neil is positioned right now, I think you need to go up the stairs, and then I'm not sure if we can physically nudge. Okay, thanks Neil. The floor is yours. So actually, let me introduce you just briefly, your bio, but while you're setting up, here we go. So, Professor Zaleva is an assistant professor in computer science at the University of Albany at SUNY. She graduated her PhD from University of California, Santa Barbara, and holds a M.Eng and B.Eng in radio communications from the Technical University of Sofia in Bulgaria. She leads the UBNet lab, which conducts research at the intersection of wireless communications and information and communications technology for development. And she is the recipient of an NSF Career Award and the Dynamic Spectrum Alliance 2019 Award for University Research on New Opportunities for Dynamic Spectrum Access. She also has the University of Albany's 2019 President's Award for Exemplary Public Engagement. She is the co-lead for the NSF-supported National Radio Dynamic Zone Partnership and Workshop Series, and is a founding member of Spectrum X. So with that, let us warmly welcome Professor Zaleva.
Thank you, everyone. Thank you, Alex, for the introduction. And can you all hear me?
Yep.
Okay, perfect. So I'll get started. So I'll talk to you today about our work on measuring and analyzing the radio spectrum, particularly with an outlook towards support of spectrum sharing technologies. So what are spectrum sharing technologies? Those are oftentimes different spectrum users who must learn to operate in the same frequency bands. And we've seen a couple emerge, mostly driven from the internet broadband community. As one example, television and terrestrial wireless television sharing with broadband internet. More recently, naval radar sharing with broadband internet. And as an emerging example challenge would be radio astronomy observatories sharing spectrum with low Earth orbit satellites that also deliver broadband internet access. So spectrum sharing has a huge potential to solve issues and gaps that exist currently across spectrum stakeholders. So for example, if you look at commercial broadband access, there's a huge unrealized economic potential for popular technologies. So for example, in 2016, in the United States, mobile wireless networks operators ran at $640 billion unrealized market deficit. And as a result, the radio spectrum has become a very expensive commodity. So a recent C-band spectrum auction in the US raised some $80 billion for just 280 megahertz of spectrum. And generally, in order to be able to sustain the demand that we offer on our wireless networks, we need to continue expanding these allocations. Through spectrum sharing, we have opportunities to solve important societal issues, such as bridging the digital divide. So what I'm showing here is for the world population, what is the fraction of connected, available but not connected, and unavailable in terms of mobile internet access connectivity. So about 51% of us can both connect and access to the internet. Another 43% could connect, but choose not to access for various reasons. And for the rest, the internet is not available through mobile means. And problems exist across all these three subgroups. So with those that are fortunate to have access and to be able to connect online, we still, operate with this market potential that we mentioned in the previous slide. And mostly as users who experience performance bottleneck, particularly as relates to emerging applications that are increasingly bandwidth hungry and latency intolerant. Yes.
I think, I'm not sure if you're sharing the right slide. We're still seeing the cover, yeah, there we go. We weren't sure if you were moving, if you had a different view.
Odd. I was progressing my slides.
Okay.
Let's see. Can you see an updated slide now?
I see Y spectrum sharing technologies. Is that the right?
Yes.
Okay.
Absolutely.
Cool beans.
Thank you. And so do you see things happening on my slide?
No. I'm
Okay.
wondering, are you in presentation mode or because we're seeing kind of like the PowerPoint interface, but not the presentation mode?
So I chose to share a single screen. Let me see if I share my full screen, whether that's going to make things better. What do you see now? You see Gather Town?
Yep. Now we see Gather. Yep. There we go.
Now you hopefully see PowerPoint, and now you hopefully see things happening. Okay.
Perfect. Awesome. Thank you.
There we go.
Thank you.
All right. So these are sort of all the things that I told you without a picture. So hopefully it will start making sense right now. All right. So we kind of covered issues with those that are connected and accessible. We hit performance bottlenecks. For those of us for whom the internet is available but not accessible, usually problems boil down to affordability, the quality of access that we can have. So internet is usually, or access is usually measured in terms of haves and have-nots. And where quality is old generation, people generally disincentivized to use because of the poor performance that they get. For those of us who are for whom the internet is not available, usually that boils down to operator incentives to deploy without guarantees for return of investment. Another direction of opportunity to grow through spectrum sharing technologies is to continue enabling critical sciences to thrive on spectrum. And these are spectrum users that go beyond, the commercial broadband realms that I discussed so far. So things like weather prediction through remote satellite-based sensing, climate science, and radio astronomy are other key spectrum stakeholders that also need to be taken into account and continue to be supported through expanded spectrum allocations or spectrum capabilities. So that the spectrum is a limited natural resource, and it's increasingly desirable by vastly different stakeholders. All of the domains that use radio spectrum as an underlying resource will better serve their users if they had more access to the spectrum. And like time, if the spectrum is unused, it is wasted. So we really need to get efficient and creative in utilizing it. So the research goal of our efforts has been to enable harmonious coexistence, as we'll increasingly need to share spectrum, while ensuring equitable access to information and communication technologies. Our efforts have been focused on 4 main directions. So measurement, and we focus on measurements both of the radio spectrum as well as more broadly of real wireless networks, sort of at a higher level in the protocol stack. Data analysis for radio spectrum as well as wireless network data. The design and development of spectrum sharing technologies for equitable internet access, and oftentimes field-based research in order to evaluate the applicability and performance of solutions that we've designed. And those tend to sort of inform each other in our work. So what I want to focus a little bit in this presentation is on our efforts to measure and analyze the radio spectrum. So key challenges in shared spectrum access emerge from a couple of applications as we increasingly have to share spectrum. So I talked about spectrum sharing networks, and questions that spectrum sharing networks have is largely relate to how do we measure and then make decisions about where in the frequency to operate, and how to continuously perform such measurements and adapt to changing channel conditions and use. Another domain that emerges with this dynamic spectrum utilization is the issue of spectrum enforcement. And questions that we need to answer there is those of a meaningful detection of spectrum activity, have and have not, or idle and occupied no longer cuts it for enforcement type of applications. We need to be able to, at a finer granularity, determine spectrum use, and moreover, understand whether spectrum is legitimately used by stakeholders. Spectrum sharing comes with large volumes of data collection that can be privacy and security infringing, so outlook towards this and care has to be taken. And last but not least, spectrum policy has to evolve hand in hand with technology, and so questions around spectrum measurement, informing of agile spectrum policy are also on the table. And so one way or another, all of these hinge on detailed understanding of the radio spectrum in time, frequency, and across geographical regions, and with the granularity of an individual transmitter. This underpins the spectrum measurement ecosystem. So what I like to think about the spectrum measurement ecosystem, I sort of split it up in physical components and functional components that support spectrum awareness. So the physical components, we have some set of target transmitters that we're seeking to measure and characterize. And we tend to do that through various sensing front ends from various software-defined radios that have been discussed so far today through higher-end spectrum analyzer equipment. And all of these gain data that can then help us characterize spectrum activity. That data can be stored either in raw or in terms of some features of interest in a cloud-based backend. On top of these physical components sit a set of functional components and their supporting data flows that ultimately support sharing applications. So as far as functional components or spectrum primitives relate to spectrum sensing, so driving the sensing front end to collect a particular data set with certain configuration parameters and granularity, followed by spectrum awareness, so broadly be able to characterize and understand activity within the measured spectrum. followed by further detail into spectrum activity, or what we like to refer to as transmitter tracking. So be able to identify on an individual transmitter level things like the modulation or location or mobility patterns of a particular transmitter. Followed by data presentation, which then feeds into those applications that we discussed earlier, such as spectrum policy and sharing networks, enforcement, and privacy and security preservation. So this is great. We need to employ this ecosystem in order to enable continuous spectrum awareness. But as we try to do that, we hit a fundamental disconnect between our requirements for spectrum analysis, for spectrum awareness, and the underlying measurement capabilities that we have today. So if you think about modulation recognition or localization, or even transmitter detection, usually those require quite substantial prior knowledge in order to be able to identify the spectrum activity. So I'm pointing with my mouse here at the bottom left corner in a green box, where we have an RF sensor and a target transmitter. And we kind of need to know what we're looking for. We need to know what's the bandwidth and have 100 overlap between the sensor's bandwidth and the target transmitter. And we need to usually know more about the underlying channel conditions, the possible supported modulation and coding scheme by the transmitter in order to be able to analyze those. So the required sensing quickly becomes prohibitive, and more so in the case of MIMO transmitter detection, where a sensor has to be at least as capable, twice as capable as the MIMO transmitter that we're looking to characterize. Hit by reality, which is sort of presented in this red box, is what available sensing we have now. So our emerging sensing systems are going to be sweep-based with sensors that are just going to crisscross a wide target spectrum and may hit transmitters either partially or alongside noise or alongside other transmitters. And that creates a completely different ballgame in terms of making sense of spectrum activity out there. So what we've done at the UBNet lab to advance our ability for seamless spectrum characterization is to essentially focus on developing methodologies that can allow us to analyze spectrum from imperfect scans, where we have data partiality, and we're geared towards both spectrum awareness, so being able to understand that there are transmitters active in a particular chunk of spectrum, particularly in the face of realistic conditions with noisy spectrum scans. And we're also focusing on transmitter tracking, particularly focusing on modulation recognition from partial and underdetermined and low-cost sensors. We develop novel machine learning algorithms, particularly focusing on robust feature design that is inspired by the wireless and digital signal processing domain and feeds into machine learning frameworks for modulation recognition. So, for example, this symmetry work that I'm showing on the right-hand side essentially allows MIMO modulation recognition with a single antenna sensor by leveraging some fractal properties of the modulation constellations. I won't get in a whole lot of detail in the time that we have, but I'm happy to talk about it offline. All right, so spectrum analytics are essential in supporting efficient coexistence, particularly important to be able to do that from imperfect data in order to allow, in the wild characterization of the radio spectrum. But where do we go from here, right? So we've walked this first step of enabling analytics. We want to get to efficient spectrum sharing. So some challenges that I see are how to allow vastly different technologies, thinking radio astronomy and commercial broadband, to coexist through measurement-driven approaches, and how to scale these measurements and awareness to hundreds of gigahertz target bands in order to understand the increasingly wide spectrum of research for different disciplines. So what we're faced with essentially is the coming tidal wave of 6G spectrum demand. So broadband, consumer broadband, is going to continue growing in terms of necessary spectrum allocation. So what I'm showing here is a sneak peek into an article that we're preparing that essentially studies the growth in capabilities and allocations for 3 technologies: consumer broadband in purple, remote sensing in green, and radio astronomy in blue. And for radio astronomy, I should note that the dark blue are allocations, whereas the rest is capabilities. So oftentimes radio astronomy operates outside of their allocations, which is great and exciting for the science. And this next plot shows capabilities in terms of instantaneous bandwidth. So in a nutshell, what we see here is that what used to work 40 years ago, where we were mostly narrowband and siloed across separate spectrum bands, is not going to cut it, especially as consumer broadband has, this growing thirst for more and more frequency ranges. Similarly, other stakeholders are growing in capabilities. So in radio astronomy, the NGVLA is going to have 20 gigahertz instantaneous bandwidth, and this is going to enable amazing science. Ultimately, we're going to end up with increasingly crowded radio spectrum, and the problem is only going to get worse. We've been able to solve our problem through exclusion zones in the context of naval radar coexistence, but it's been quite inefficient. Like in the context of CBRS, for example, about 60% of the US population would reside in exclusion zones. Similarly, if we were to create exclusion zones for radio astronomy protection, commercial broadband through low Earth orbit satellites would also largely be affected by exclusion zones. All right, so not the answer. We have to be able to do something more dynamically. Luckily, those different stakeholders are increasingly coming to the table and trying to create frameworks in order to understand how to coexist. As an example, radio astronomy talking to SpaceX low Earth orbit satellites in order to understand how they can coexist on spectrum that is currently actively being used by radio astronomy for science. And it is challenging as we have different success measures across the 2 disciplines, different capabilities, but the same long-term objectives to maximize the use of spectrum. So I know I'm running over my allocated time, but I want to leave you with this question. So the question of how to facilitate mutual understanding, trust, and experimentation in support of these spectrum coexistence issues across different stakeholders. And I want to just quickly make a plug for an initiative that I've been participating in on scoping national radio dynamic zones, sort of these test beds that will allow coexistence and experimentation across different stakeholders. And just a plug for where you can find archival material where we've essentially looked to create cross-community educational opportunities across remote sensing and radio astronomy and the active commercial broadband community. Blue Sky's discussion about what might experimental capabilities look like in order to enable these coexistence advances. And yeah, I'll stop here, and I'm happy to answer any questions now if we have time, or I'll be around later as well. Thank you.
Thank you. Thank you. I'm not sure. I think maybe well, how about we entertain one question? Obviously, if you're here afterwards, we do have a networking session. But how about one quick question? Mike, would that work?
Thank you, Dr. Zaleva. It looks like Alex might be having a network connection. See, his network is a little bit poor, but we appreciate it. I think we might wait. Actually, we could probably do a couple quick questions. If anybody has questions from the audience, you can come stand up here to queue for questions.
Yeah. So where like Mike is located, just head on down. Any
like Alex might be connecting now.
This is a very realistic kind of experience. You actually have to walk to somewhere to talk or ask a question.
But we still get the benefits of a virtual environment where there's slight disconnects and audio issues.
Yes, absolutely. And I'm sorry about my technical issues too.
No, we really appreciate it. It looks like no questions at this time. We might open up for questions at the end for the set of all 4 speakers. But thank you very much for your time. Really appreciate it. And I'm sure we'll have people walk around and ask questions as the day goes on.
Awesome.
Yep. Thank you.
Thank you. Mike, can you hear me? Mike, can you hear me?
Alex, are you back there? Looks like, oh, there we go.
Can you hear me?
Yep, now we can.
Okay.
We're looking good.
Okay.
All right.
Yeah, like what time is it? 2:20? That's about right. Well, like when yeah, no, just kidding. So that was an awesome presentation. So thanks to Professor Zaleva for that insightful presentation, especially on the radio dynamic zones. So next up, we have Ryan Bowles, Dr. Ryan Bowles from MIT Haystack Observatory, and just a quick introduction in terms of his background. He is a research scientist at MIT Haystack Observatory, very interested in signal processing, statistical estimation, novel instrumentation applied to radio science. He earned a BS in aerospace engineering from Penn State, MPhil in engineering and control systems from Cambridge, and an MS and PhD degrees in aeronautics and astronautics from Stanford in 2015. He and colleagues at the University of Colorado Boulder developed the Zephyr Meteor Radar Network, a novel MIMO system designed to estimate 3D wind field and in the upper atmosphere by way of meteor trail scatter. He has contributed software and signal processing algorithms to the Aero and Vista CubeSats, which will launch in 2023, with the goal of locating and characterizing auroral emissions using electromagnetic vector sensors. So with that, let's warmly welcome Ryan Bowles.
Thanks, Alex. Can you all hear me? And the slide switching works?
Yes, yes.
You see that? Okay, great. We're ready to go. All right, so thanks for that introduction. My talk's going to be on measuring winds at the edge of space with the Zephyr Meteor Radar Network. And I'm going to start off on the science side, but I swear we will get to SDR by the end of it, so you'll see the connections eventually. But I'm going to start with some definitions. So what is a meteoroid? What is a meteor? What is a meteorite? These things are often confused in the public. A meteoroid is a solid body in space that is small and moving fast relative to the Earth. And these are exponentially more common as size decreases. A meteorite is a body that survives passage through the atmosphere and lands on the Earth. You can see a little picture of iron micrometeorites in the bottom left here. And then a meteor is the phenomena, which includes light and also plasma, that is caused by a meteoroid entering the atmosphere. And typically these form at altitudes between 70 kilometers and 120 kilometers. So most people are familiar with meteors as shooting stars. And you can see this video here with a rather spectacular fireball. Most shooting stars are not like that. But in actuality, meteors are much more common than the ones you actually see. And they're always forming plasma up in the upper atmosphere. And we can detect those meteors with meteor radars. And as I already mentioned, meteors from sporadic micrometeoroids happen all the time. These are not just things you can see. Dust particles are always impacting the Earth's atmosphere, creating plasmas, and we can scatter off those plasmas. And so this, in the background, is an image of the McMurdo meteor radar in Antarctica. This is a traditional, typical meteor radar. These typical meteor radars are monostatic, which means the transmitter and receiver are located in the same place. And they use a pulsed waveform, so it sends out a pulse of energy and then listens for that pulse to be returned. They have an interferometric receive array to calculate direction of arrival, so from where that signal is reflecting from. And scientifically, they give a wind averaged over the entire field of view. So they're measuring winds in the upper atmosphere. We'll talk about how that happens. And how this works as a scattering mechanism is what we call specular scattering from the trail plasma of the meteor. So you can imagine a meteoroid coming in to the atmosphere. It's descending in altitude quite rapidly, and it's leaving a trail of plasma in its wake. And we can reflect HF radio waves off of this trail of plasma much like a mirror. So if your monostatic case, your transmitter is where your receiver is, and you send out a signal, and the trail happens to be perpendicular to the direction of travel of that wave, it'll reflect it right back to you, and you'll see that reflection off the meteor trail. You can also have bistatic configurations where, if your receiver's in a different location, you'll still be reflecting off the trail like a mirror, but you won't necessarily be looking. The trail doesn't exactly have to be perpendicular to where you're looking in order to see it. The key thing, though, is that these trails in the upper atmosphere are moving along with the background wind. So the plasma is moving with the wind, and the reflection of that moving trail imparts a Doppler shift on the signal that we're sending and receiving back. And so we can measure that wind velocity through that Doppler shift. And this gives us a way to probe winds in the upper atmosphere. We can also relate the diffusion of the plasma to temperature, but that's a bit more of a sketchy measurement. So we like to stick to winds most of the time. So as far as an actual radio signal, what you see with these meteor trails falls into two camps. There's underdense echoes and there's overdense echoes. So an underdense echo happens when a trail plasma frequency is less than the radar frequency. And so that's trail density is less than the frequency that you're transmitting at, basically. And if we take a slice of the returned power corresponding to the range that you're seeing that meteor at, this is what you'll see on this bottom left here. You'll see a quick increase in power. That's the meteor trail appearing in the sky. And then it almost immediately exponentially decays back down to zero. And what you get with an overdense echo, which is where the trail plasma frequency is greater than the radar frequency, is you get this quick rise, but it has kind of a flat portion where this plasma frequency is still greater than the frequency that you're transmitting at. And then once that plasma frequency drops because the trail is dispersing, you see that exponential decay again. And so by measuring Doppler shifts off of these signals, that's how we're getting the wind measurements. And this is just another example of a real meteor radar echo. This is taken with that McMurdo meteor radar in Antarctica. And this is also just plotting not only just the power that you're receiving from this single range gate, but also the phase of that signal in that range gate. So you can see, this phase is shifting over the period that we're viewing this trail, and that's where we're getting this Doppler shift measurement and giving us line of sight velocity. So I mentioned the word sporadic meteors earlier. We call them sporadic because they happen basically randomly, and they occur randomly in space on the Earth's surface and also in time. So if this is what we're plotting on the left here is just detections of meteor trails and their locations. And this is showing basically that when we're running a meteor radar network, this one's over Germany, we see these trails popping up spatially uniformly. And then in time, they're also random, but they do have some correlations with local time. And there's actually diurnal and seasonal patterns with a peak in meteors around sunrise and the trough near sunset. And this happens because what we like to call the bug on a windshield effect. Think of the Earth as your car, and it's moving through space, which is, you're driving down the highway, and we're basically hitting the most bugs on the front of our windshield. So when we're at 6 a.m. local time, we're pointing down towards the direction of travel and catching most of these meteors. So meteor radars operate at HF and VHF frequencies, and why is that? Well, there's a minimum of about 15 megahertz that we can operate at, and that's due to the typical peak ionospheric density. And so if you go lower than that, you have issues with refraction of your signal or even reflection off of the ionosphere that will make it very hard to determine if you're actually reflecting from a meteor. So we want to stay well above 15 megahertz. But we also want to stay below about 40 megahertz due to what's called the ceiling effect. And this happens because of those underdense and overdense echoes that I pointed out before. You get far fewer detections when the meteor trail is not dense relative to the frequency that you're transmitting at. And the density of the trail is proportional to the mean free path in the upper atmosphere. So that decreases rapidly with height. The mean free path increases rapidly with height. And so you're seeing fewer and fewer meteors as you get higher and higher up because it's less dense plasma. And so you can see on this plot on the right here, once you get above, say, about 40 megahertz, you're losing a lot of meteors at the upper heights because they're not dense enough for you to see them. And so what you end up doing is picking the sweet spot in the upper HF, lower VHF band around 30 megahertz, where you can get the most detections possible and you can get them at a wider range of altitudes. And so typically we're seeing meteors at the heights at which they form in the upper atmosphere between about 80 and 100 kilometers altitude with good counts. And there's that rapid fall off above 100 kilometers is due to the ceiling effect. Okay, so I already mentioned that the trail plasma drifts with the neutral wind and that this movement imparts a Doppler frequency shift in the direction of what we call our Bragg vector direction, which is just that perpendicular to the trail direction that we're reflecting off of like a mirror. And we can relate that measured Doppler shift to the wind at the meteor location and time. This is just like a dot product between our Bragg vector and the 3 wind components. And you divide by 2 pi, and you get the Doppler shift frequency that we can measure with the signal that we're recording. And so you can imagine, bouncing off of a bunch of meteors at different diverse locations over your head, and fitting that diverse set of measurements within a given volume. You can derive the wind components: the zonal wind U, that's east and west, and the meridional wind V, that's north and south. And then there's also a vertical component, which we usually assume to be 0. And so by collecting all these measurements, averaging them together, you can make plots like this with the zonal and meridional wind, and you can see clearly these tidal features where the wind's shifting back and forth twice a day, much like the ocean tides. All right, so that's all about traditional meteor radars and how they work, but we want to take the technology to the next level, and so we're doing that with coded continuous wave networks. And so a coded continuous wave technique uses transmitters that are continuously transmitting, and they're using independent pseudo-random binary phase codes. The receivers can decode the signals from multiple transmitters, and they know which transmitter's transmitting because they know the codes that each transmitter has, and they can correlate with them. And so you get a combinatorial number of links all over one frequency. So the advantages of this over traditional meteor radar are you get far more detections, and that's because of the variety of specular geometries. You're not blind to as many meteors because you're encountering more of these perpendicular trails where you actually see the reflections. You don't get any range aliasing because this is not pulsed, this is continuous wave. And you get a non-degenerate wind field sampling. So whenever you combine multiple meteor radars, you can now measure the full wind vector instead of being blind to any components that are perpendicular to the direction that you're looking in. So normally with a single meteor radar, any wind components that are swirling around your location, basically you can't see because you can't see any Doppler shift in that direction. So we can take that one step further, these continuous wave pseudo-random coded networks, and talk about MIMO meteor radar, where now instead of using a single transmitter with a receiver array like what a traditional meteor radar would do, now we can talk about using a transmitter array where each of those transmitters is transmitting its own unique pseudo-random code, but they're laid out in an array, and then you can receive that signal, all of them, with a single receiver antenna, and do all of the decoding for each of those antennas in the processing at your receiver, and do the direction of departure calculation all at the receiver. And so that lets you concentrate a lot of the complexity of building this network at your transmitter sites, and lets you get away with rather simple receiver sites that are just a single antenna and single receiver computer. You can even go to full MIMO configurations where you have a transmitter array and a receiver array, and that gives you independent direction of arrival and departure estimates. and that can help you fix the location of the meteor with much more accuracy. So once you have this kind of MIMO meteor radar technique with these coded continuous wave networks, and you can build a full network out of them, that gives you enough information not just to estimate the averaged wind overhead, but to give you the full 3D wind field as a function of time. And so that's what these plots are showing here. This is with a trial system called Simone, which was in northern Germany, where we put together this kind of MIMO meteor radar network and used it to calculate these wind fields. So this is slices at 90-kilometer altitude. This is 3 different times at 5 local time, 8 local time, and 11 local time. And the colors in the background here are showing the horizontal wind speed, and then the arrows, the streamlines, are showing the direction of the wind. And you can see a single meteor radar averages over this entire horizontal span. But now we can start to see how the wind is changing at different locations, which gives us a much better window into what's happening scientifically up at those atmospheres, up at that altitude. And we can take that slice and move it up to 96 kilometers, and we can see the winds are completely different there, even at the same times. And so there's lots of information here that we can use to learn about the upper atmosphere. And we can also plot this differently, and instead of looking at the horizontal maps of the winds, we can basically sample any location and look at those traditional zonal wind and meridional wind plots. And you can see, again, these tidal signatures, but how they're actually slightly different at each of these locations. And again, that's giving us a view into the physics that we didn't have before. So why is all this important? Why do we care about using meteor radars to measure winds? Well, it's because this upper layer of the atmosphere where the meteors form, which is the mesosphere, and the lower thermosphere, which we call the MLT region, it's hard to measure because in situ measurement is impractical, right? It's too high for balloons, and it's basically too low for satellites. Any satellite operating at these altitudes is going to come down to Earth within a few orbits. So the only way that you can really measure this is with remote sensing techniques, and our current remote sensing techniques are very sparse. We're not monitoring much of the upper atmosphere in this way. And the neutral atmosphere is particularly difficult to monitor because, we can't scatter off of it like we can with plasmas. And the frontier of research in this area is looking at system science. So we want to model the whole atmosphere, and that requires getting an entire view of the system. The models need more constraining data in order to do that. And there's actually, lots of effects that travel up from the lower atmosphere and from the upper atmosphere that all couple into what's happening at these altitudes. And we don't really know what all these dynamics are because we just don't have enough data. So we want to be able to measure the energy contribution that's coming from below in the full wave spectrum by sampling in time and space better than we previously have. So that's why these meteor radar networks are important. And so they are important. So we're trying to build out these meteor radar networks with something called the Zephyr project. Well, this is a National Science Foundation project where we're developing and building a distributed MIMO meteor radar network for observing the upper atmospheric winds that can support a future large-scale deployment. And this is a joint project between MIT Haystack and CU Boulder. We're building a network out in Colorado, Zephyr, Colorado, that will be located near CU Boulder and covers the Rocky Mountain region. It'll have 2 transmit array sites, 1 receive array site, and 12 single receiver sites. But we're also planning a companion project to build a Zephyr Millstone network that'll be around MIT Haystack Observatory. We'll have a transmit array at Haystack, and we'll be putting some single receiver sites out in the New England area. This is just a notional network. These dots don't mean anything yet. These were just places where we thought, hey, we might know somebody there, we'll put a dot there. But partly why I'm giving this talk is that if you're interested in kind of operating a receiver site, come talk to me, and in the next few years, we might try and make that happen. And so, in order to be able to build these networks and make them sustainable, we're taking this approach of putting all of the complexity in the transmitter sites. So the backbone of the network is composed of transmit array sites that require more infrastructure, more space, more power. And where possible, try and co-locate those with other instruments. But way that you then have to fill out the network is by surrounding those transmitter sites with receiver sites. And those can be single antenna receiver sites that require less infrastructure. And that's a great way to engage with schools and amateurs in order to fill out the network. All right, so how do we grow meteor radar networks sustainably and efficiently? Well, we're going to use software-defined radio. And that allows adaptable and upgradable processing, and it allows us to experiment with building out these networks and make them better over time. We have modest requirements for our SDRs. From least to most constraining, we only need about 1 megahertz bandwidth because that's about all we're transmitting with actually 100 kilohertz right now. The frequency coverage needs to be around 30 megahertz because that's where meteor radars operate. But the big thing is that we need GPS time and clock sync in order to be able to, match the received signals with the timing of the transmitted signals and get actual ranges towards these meteors. And so that is currently what's very limiting as far as SDRs right now. Not as many have this ability to sync the timing and clock, but hopefully that'll get better in the future. And we're also using open source software. So our philosophy behind this is that it allows us to pool effort for higher quality and easier maintainability. A single entity is a bottleneck, and a community gives you scalability. And we want to encourage educational and amateur participation, so we're going to try and make our software easy to install and fun to use. None of this software actually exists yet, but we're working hard to develop it. And so long term, we're building out this network in Colorado. We're building one at MIT Haystack Observatory. But what we really want is continuous coverage across the US and across the world so that we can measure meteors and upper atmospheric winds all the time. And that's going to require quite a big network and lots of participating receiver systems. So that's why we want to make this easy to scale. And probably went a bit over my time, but I'll take any questions if there are any. Thanks so much.
Thank you, Ryan. I think we're going to save questions till the end because we are kind of running a little bit behind schedule. But thank you. That's really awesome. If we can spread SDR across the entire country like that, that's like all part of the plan.
Yes, of course, these radios could do a lot more than just meteor radars once they're there. So
exactly,
you can have evil plans to do more than that.
Like they shoot lasers too. Excellent. Next up is we have with us Dr. Nathaniel Friesel from the University of Scranton. And Nathaniel, he's an assistant professor of physics and engineering at the, let me just double check this. Yep. At the University of Scranton, and he's also passionate about radio and radio science ever since middle school, and also an amateur radio hobbyist through scouting. He earned his BS in music education physics from Montclair State University and his MS and PhD degrees in electrical engineering from Virginia Tech while working at the Virginia Tech Super Dual Aurora Radar Network, or SuperDARN Laboratory. Nathaniel has founded and now leads the Ham Radio Science and Citizen Investigation, or HAMSci, Citizen Science Collective, and he's the principal investigator for an NSF-funded HAMSci Personal Space Weather Station project, and is the recipient of an NSF Career Award in the study of traveling ionospheric disturbances. He is the advisor for W3USR, University of Scranton Amateur Radio Club, and is the winner of the 2017 YASME Foundation Excellence Award, as well as the 2019 Dayton Amateur Radio Association Amateur of the Year Award, and the 2021 inductee of the CQ Amateur Radio Hall of Fame. So with that, let's warmly welcome Nathaniel.
Thank you so much, Alex, and thank you, everyone. Today I'm going to talk about what's called HAMSci research with software-defined radios. And as Alex said, I really got my start in amateur radio. So this is one of the amateur radio stations I set up at my house when I was much younger, before I knew I was going to do this as a career, basically. And I was always really fascinated with how you could use these radio systems to communicate so far around the world. And now I'm able to go back, and of course much of this equipment is replaced by software-defined radios now, and we're able to use that to actually study what's going on in the upper atmosphere and in space. And so from my amateur radio background and also from my training at Virginia Tech studying to get my PhD in electrical engineering, I formed this group called the Ham Radio Sciences Investigation, or HAMSCI, and we're a collective that allows university researchers to collaborate with the amateur radio or ham radio community in scientific investigations. And we want to advance scientific research and understanding through amateur radio activities. We want to encourage the development of new technologies to support this research and provide educational opportunities for the amateur radio community and the general public. So before we get on to looking at the measurements too much, I just want to review a little bit about the ionosphere and how certain radio frequencies can travel so far around the world. So the ionosphere is generated by solar, ultraviolet, X-ray energy ionizing the upper atmosphere and creating this electrically charged layer, which you can see here in the colors. And then if you use the correct frequency, usually frequencies between about 1 and 30 megahertz, the high frequency bands, you can get refraction back to Earth. So you might have this station in California transmitting to my station in Pennsylvania, and the signals can go up and bounce, and this lets you go around the horizon. In this particular movie, you can see how the diurnal effects or day-night effects impact the ionosphere. So at night you have less ionospheric densities and you get less refraction at 14 megahertz. As the morning comes back, you go back and transition into morning, you can see that the ionosphere builds up again and you get, once again, get more refraction. So this, by listening to the signals that you receive over here, and you can tell certain things about about the medium, about the ionosphere that the signal traveled through. Conversely, it's also good to know that you get varying amounts of refraction based on what frequency you use. So in these two plots, you have identical background ionospheres, but we're using two different frequencies. So if you go to a higher frequency like 15 megahertz, you might be able to go 1,500 kilometers in a single hop, whereas if you go to 10 megahertz, it might be 2 kilometers to go that same distance. So by varying the frequency, you're able to sense different parts of the ionosphere. So I was told from talking to some of the organizers of this group that many of the people in the room here might be familiar with a lot of the very technical aspects of how software-defined radios work, but they may be less familiar with some of the more amateur uses that SDRs are being used for these days and some of the amateur solutions. So I wanted to highlight one of them, and that's the Kiwi SDR. So this is a software-defined radio receiver that is running on a BeagleBone. It goes from about 0 up to about 50 or 60 megahertz, and it's fully networkable so that you can plug it in, and then immediately it can show up on this map if you go to map.kiwisdr.com. And the really powerful thing is, anyone who has access to a computer can go to map.kiwisdr.com and they can click on any one of these Kiwi SDRs, and they can immediately it's as if they are sitting in front of an HF radio receiver, shortwave radio receiver at that particular location. You don't need to log in. You don't need any credentials. You can just go and watch the radio spectrum and listen. And so this is an incredibly powerful educational and scientific research tool. So this Kiwi SDR network is fantastic. I have one set up at my house over here in this little room, and I just have it connected to an antenna kind of like this one. That's a G5RV. And here is an example of a web interface for the Kiwi SDR. And you can see the waterfall display here. And I'll just play you this recording so you can hear what some of the audio output sounds like. So here I'm listening to a station in Lithuania from Scranton, Pennsylvania. Let's see if it that.
Thank you from Lima Yankee number 3, number 1 Alpha. QSL station from New York. Whiskey Echo 2 Charlie Alpha Tango 59 Candlelight John. January, October, November. Good morning. Okay, Sussex County, New York. State.
So you can hear that it's still a very noisy signal. It's one of the very interesting things about HF communications. You can still have very noisy channels, but these noisy channels can have lots of good information that can tell us about the ionosphere. So yeah, here's where I received the signal from, and that's where it was transmitted from. So where do software-defined radios come into play here? Where are some other places? Amateur radio operators, they can still communicate via Morse code, and one of the neat technologies that came out of SDR over the past few years is amateurs have developed ways of simultaneously recording all of the Morse code transmissions on an amateur radio band all at the same time, and there are radios that can do it on receive these things on all the amateur bands simultaneously, and then software can decode this information, and they will report it in real time to this website called the Reverse Beacon Network, and the RBN keeps track of who was sending the signal, who received the signal, what frequency, what time, and they archive all of this information, all made possible by software-defined radio. Similarly, there's a website called WhisperNet and PSK Reporter that are also observing amateur radio transmissions, often using software-defined radios, but these are using digital transmissions instead of Morse code. All three of these systems have been running since about 2008, and they're all recording all of the data that they see. It's available in real time from their websites, and there are ways that you can go onto the website and you can either download the archival data or you can contact the operator, and they will graciously provide it to you. And what's really neat is that you can actually see space weather effects right in this data. So here's an example of that. This is from September 6, 2017, and I took the data from the RBN and the WhisperNet systems, and I looked at it at a period 15 minutes before a solar flare happened and 15 minutes after. So this is the period 15 minutes before the solar flare. Every line you see here is a communication that was observed by either an RBN receiver or a WhisperNet receiver, and it's color-coded by frequency band. You see most dominantly the green is 14 megahertz and the orange is 7 megahertz. And before the flare, there were 12,824 observed paths. As soon as the X9.3 class solar flare took place, you can see that the number of communications dropped immensely down to only 2,293 paths. And so this is because with the solar flare, you get a sudden increase in ionization in the D region ionosphere, which is the layer that's closest to us on the ground. In that particular layer, there's a lot of neutral particles in addition to the electrons and the ions. And so you get this collisional damping where the electrons will collide with the neutral particle before they're able to re-radiate the signal, and that causes this absorption effect. So that's why you're seeing this sudden drop in signals. And you can plot this in a number of ways. This is from that same event. There were actually 2 solar flares on that day. I split the data up. So in this panel, we're looking at Europe, and then this is on 7 megahertz. And so on the y-axis here, you have the distance between transmitter and receiver going from 0 to 3,000 kilometers. And on the x-axis, we have 12 hours worth of data here. And so you can see in Europe, here's the first X-class flare. It just totally knocked out the communications. It recovered fairly quickly, but then you had another flare, and that was even larger, and that knocked out communications even longer. It took longer for the ionosphere to recover. But it's really neat that you can see this just in the amateur radio communications. The United States was less affected by this because it was actually in still in nighttime. So the white dashed line here, this is showing you the solar elevation angle. And so when it's highest, that is when you're at noon. So during the night and going into dawn, you really don't get much of an effect because the Earth is shielding the ionosphere from the effects of the solar flare. But it's really neat. You can see this in that data. So as is mentioned in an earlier talk, one of the key issues that we need software-defined radios to have these days is really careful GPS or GNSS timing and frequency stabilization, frequency references. And you need that in order to be able to do things like make correlations with radar systems and things like that. So the observations I just showed you here, these are all very noisy, very amateur observations that don't have any of that sort of careful clocking. But we are working, the HamSci group is working on developing a system that would include some of these much more careful measurements. And we're calling this a HamSci personal space weather station system. And the idea is that this would be a ground-based system that could observe many different space weather effects. And a large part of it would come from a software-defined radio that would take in, raw IQ data. We would want it from 2 different channels so that you could look at, say, X mode and O mode polarization. We'd want those all to be phase locked. We'd want the GPS or GNSS discipline oscillator and timing in there, and we'd use that as a way of as a tool for sensing, making the measurements that we need. We'd also, with this system, we don't want to just observe radio. We're also interested in observing the Earth's magnetic field. So we have a ground magnetometer in here. We're also interested in very low frequency radio receivers as well, and also possibly adding additional instrumentation. So for instance, if you're up in like a high latitude region, you might want to add say an auroral camera. So we're working on developing this right now. I have the group TAPR, which is an amateur radio engineering organization. They're developing a new software-defined radio called the Tangerine SDR, which is going to meet these requirements. So it's similar in a lot of ways to the EDIS systems, but again, it's paying a little bit more attention. We're trying to make it more accessible to the amateur market here. So I want to point out a couple more things. This is another screenshot of a Kiwi SDR. You can see every once in a while you get a slash like this. This is actually a chirp ionoson that we can see that's it's sweeping through frequencies to measure the ionosphere. So Juha Virinen has developed some code that lets us decode those into ionograms. So we're working on getting that to be implemented in our personal space weather station system. Another thing that's very useful for studying the ionosphere are looking at Doppler shifts. So if you have a very stable frequency reference like WWV out in Colorado, if you're able to have a GPS locked receiver and you're able to measure very small frequency changes in the WWV signal, say like 0.1 to 0.3 hertz changes, you can actually see effects of the ionosphere moving up and down or changing densities. And so that's the sort of thing we see over here. This was taken during the eclipse in 2017. This station in Milwaukee, Wisconsin was listening to the WWV receiver in Colorado, and you could see there were positive Doppler shifts in the morning, negative Doppler shifts at night, and then the eclipse gave the opposite effects. So there's a lot of interesting things we can do with this. Thank you very much.
Awesome. Thank you. Thank you, Nathaniel.
Thank you.
Thank you. Next up, it seems like we have like a lot of complementary topics and covering different areas and such. And we're gonna end at the fourth and final presenter we'll kind of look at things from a sort of an IoT perspective. So, you know, like that diagram that Ryan showed, like in the previous slide, with like every square inch of the United States being covered by, you know, by an SDR. Our next speaker could potentially help with that, which is Professor Basima Islam. So, Basima, come on down. So no, this is very exciting. Thank you, Nathaniel. Thank you, everyone. So, so let me introduce Basima. So yeah, yep, there we go. Yeah. Ta-da! Okay, Basima, can you hear me?
Yes, I can.
Excellent.
Hello.
And I can hear you. Perfect, perfect. So Professor Islam will be joining the Department of Electrical and Computer Engineering at Worcester Polytechnic Institute as an assistant professor this fall. So we're eagerly waiting for Basima to land. Although, just truth be told, like we've been, I think, like you've been visiting campus quite frequently, before that. So we're just really excited to have you join us. She will direct the Bringing Awareness Through Systems for Humans Lab, or BASH Lab, which focuses on the understanding and enhancement of usability, intelligence, and processing capabilities of tiny, low-powered edge devices to realize their full potential in our daily lives. She aims to develop new set of intelligent edge computers that will develop sustainable and scalable sensing solutions in variable applications domains ranging from health wearable to precision agriculture. And the Professor Basima engages in a lot of interdisciplinary research with involving things like, for instance, machine learning, mobile computing, embedded systems, and ubiquitous computing. And her work has been published in several top conferences, including IMWUT, UBComp, IPSN, RTAS, and MOBISys. In recognition of her work on time-aware intermittent systems, she received an honorable mention at the Gaetano Borello Outstanding Student Award at UBComp 2020, and being one of the rising stars in EECS 2020, she received an N2 Women Young Researcher Fellowship in 2017. Forbes named her one of the 30 most influential scientists under the age of 30 in 2021. And Basima received her PhD in computer science from the University of North Carolina at Chapel Hill in 2021, and is currently a visiting postdoctoral research associate at the University of Illinois at Urbana-Champaign. So with that, let's welcome Professor Islam.
Thank you very much. Thank you very much, Alex, for the introduction. Hello, everyone. Can you see my slides?
Not yet. Not yet.
Okay. Because it's not letting me select the window that has the slides in.
Are you using a Mac?
Yes.
Okay, so I suspect what happens is Mac is showing one screen, but I think you might have to share the whole desktop and then present the slide in full screen mode in order to work. I'm not sure if there's a workaround around it, but yeah, Gather seems to be kind of finicky that way.
Okay. So let me know what you were saying now. Okay, I think this is better. How about now?
I still, I don't see anything. Actually, yeah, right now, I don't think you're sharing anything.
Okay, that's interesting because it's showing me I am, and now it's not letting me share anything.
Let's try one more. Let's try one more time. That's what happens when we have an interface that looks like Zelda. It's like.
Okay, let me see what I can do. Sorry for the technical difficulties, everyone.
If you want, like, let's. Okay, so let's see. All right. All right. So while we're waiting, Obviously we are going in a little bit into overtime in general into the networking session. So we'll try and start promptly with the first technical, breakout sessions at like, shucks, what's the schedule? 3:15. Yeah, 3:15. So obviously we'll need to move that a little bit, and we'll probably like go into the networking session at like 4:15. Like just yeah, because of the delay. So there we go. Mike. So let's give this a try one more time.
Yep, sorry, I was in the.
Yep.
Is there an issue?
Yeah. I think Basima's on it, but actually, yes.
Looks
How about
Let me
now?
see. Yes. Well.
Just need me to get back in the room. That's all.
Yeah, exactly. Like we don't see it in presentation mode, but.
Okay, let me try it again. How about now?
Yes.
Perfect.
Great.
Awesome. Thank you.
Thank you so much, Michael. All right, everyone. Sorry once again for the technical difficulties. So my name is Basima. I'm an incoming assistant professor in the EC department at Worcester Polytechnic Institute. And today I'm going to talk about this vision, which is called Sustainable Intelligent Everyday Objects. So we are saying that whatever we use in our daily life, starting from the clothes we wear, the shoe we wear, to the pen we use, in the future, they will all become intelligent objects with a goal to make our life better. And to do that, computing is getting integrated into it. So this intelligent everyday objects will not only help us in our personal life for our health, it will also be useful for monitoring the environment and making the environment more sustainable. And they will be used for monitoring our home and to help us avoid some difficulties or avoid some situations like we don't want to avoid. Like if there's a fire and we are away from the home, we want to get notified as soon as possible. So this vision of intelligent everyday objects is coming towards a reality because very recently ARM has published a white paper, and they announced that we will be having 1 trillion IoT devices by 2035. And IoT devices, or Internet of Things, are the core of the successful everyday object vision, intelligent everyday object vision. Now, this is nice, right? We will have 1 trillion of IoT devices where most of these devices are powered by batteries. Okay, then there's a lot of battery. If you think about it, 1 trillion devices that gets powered by battery. So you have to change batteries of all those devices. So you have to replace it or even recharge it if you have a rechargeable battery. So let's look at some number to identify like how big are we talking about. So let's say a battery can last for 10 years. If that is true, we will be replacing 274 million batteries every single day. That's a huge number of batteries to change all around the world. Now, these batteries have always been a bigger bottleneck for the IoT industry. And not only that, it is ecologically unsustainable, right? And where will you, what will you do with these 274 million batteries? Will you throw it in the environment? What are you going to do? And recycling, the batteries have not yet been perfected, and they result into a lot of hazards. So let's look at this whole thing from a different point of view. How about we remove the batteries from the IoT devices whenever possible? So we are not saying, hey, we are going to remove the battery from everything. No, whenever it be possible, let's remove the batteries and look at the ambient energy around us, like solar, the kinetic energy we generate, or even the Wi-Fi we use. Can we use these renewable energy sources to power these IoT devices? And if we can do that, that will enable us to have sustainable lifelong sensing and computing, because there's always ambient energy around us, and theoretically these devices never have to die. So they will always be sensing and computing of the environment. That's good, but where will we use it? The application domain is actually wide. It ranges from continuous health monitoring, like blood pressure or blood sugar monitoring, to biodiversity preservation, or even catastrophe prediction. Now, to realize this vision or this goal of getting the sustainable lifelong sensing and computing, the research community has divided into two areas. They have focusing into two lines. The first domain is called zero power passive communication, or backscatters, where we take the RF energy or RF transmissions that happens all around us in TV spectrum, in Wi-Fi spectrum, in other spectrums, and try to sort of piggyback on top of the existing RF transmissions to send some information. The second line or the second domain is called zero power on device computing. And this area looks at, hey, if I can harvest some energy from the environment, and instead of sending the raw data, which is often larger in size, can I do some processing, get the output, which is usually a smaller size, some bits, and then use the zero power passive communication to send the output. That way, it is often more responsive because the backscatter technology is yet to have the throughput we have with active radios, but it is still doing great in terms of computing in the small devices. So today, what I'm going to talk about mostly focuses on how we can achieve this zero power on device computing, what are the challenges, and what it lies in the future. So let's take a step back and think how Internet of Things work. So Internet of Things, usually what they do, the current devices, they collect data using sensors and actuators. They send this data to some cloud server where this computing or processing of the data happens, and then it comes back. Recently, what is happening as there is the security challenges, there is this delay challenges, and to solve it, we are thinking about, okay, what if we bring the computation a little bit closer to the actual sensing? And that's where the edge devices come in. The edge devices does some early data analytics, so it can provide some output if needed the whole. If needed, then it can go back to the cloud server to get more processing done. But what we're trying to say is that this is not enough. Why? Because we still have a limited network bandwidth. The network is, the spectrum we have is a physical number. We cannot generate more spectrum. We can manage it to make sure everyone can work, but we cannot create spectrum out of nowhere. And also the communication energy cost is often high in these batteryless systems. So we are saying that, okay, we're going to do computing on this device. We will still communicate the output, but not the whole data. We will do the processing on the device itself. Now, these devices often have low processing capability to ensure that it can run in this lower energy footprint. It also has a small memory footprint to support that, and it has limited energy because it often does not have the batteries to work with. Let's call this the extreme edge devices, right? So what are the main challenges of the extreme edge devices? The first one is the energy constraints, that the ambient energy we often have around us are not sufficient to power these devices directly. So we have to wait to charge our energy buffer and use it. Then there's a processing constraint because we have microcontrollers that has lower processing power. And finally, we do not have any control of the ambient energy around us. I cannot control when it's going to rain or when it's going to be a sunny day based on my need. We have to work with what is we are getting from the environment. So given these three challenges, the vision is that we will develop a new set of sustainable edge computers that are reliable, that are intelligent, self-evolving, programmable, and user-friendly. So I will go over each of them, why they're needed very briefly using this example, which is taken from an existing project by IBM, which is called the Project Rhino, where the goal is we want to stop the poacher from poaching a rhino. So what the system does, it monitors a bunch of impalas who has the same food habits as the rhinos to see that if we can, if there is a poacher in the area, inform the forest ranger who can stop the poaching. So if such a system is not reliable, the information that goes to the ranger will be often wrong, and they won't be able to reach the poacher in time to stop the poaching. If it's not intelligent enough, what will happen is the information might mislead. So the forest ranger might go to a different location, or even have so much wrong data that at one point they get frustrated, like, okay, I'm not gonna use this. This doesn't work. So it needs to be intelligent enough. Then it needs to be self-evolving, because the impalas, their behavior, the environment around them changes, they do migrations. There's going to be programmable, because we don't want to go every year to find those impalas and provide any software updates to the systems. So it needs to be able to be programmable. And finally, it needs to be user-friendly for both the impalas and the forest ranger. So this idea of sustainable lifelong sensing and computing, to realize that, I'm going to talk about a fork that is called time-aware intelligent intermittent system, where we will start with what is intermittent computing system. I just say that word, but what does it mean? So often in an energy harvesting system, you do not get power all the time. And for here, when the cloud is blocking the sun, we do not have the energy to power up the system, so the system goes to power failure. And in a traditional computing system, this power failure will lead to a non-termination, so we will be repeating the same task again and again. To avoid that, to avoid this hinder of code progression, code execution, there are techniques like checkpointing, the stars bus model, that helps us to recover from power failure and not restart, but resume. And the research challenge, what I'm going to describe, is this. So let's say we have this 2 tasks, and we have a battery power system, a persistently power system. We can finish this task within a given deadline. Now we have intermittent power. As a result, we are missing the deadlines. Okay, but how can we ensure that we do not miss deadline, because we do not have enough power? The solution lies in approximation. So if we can divide each task into mandatory and optional portions, where completing the mandatory portion time is sufficient, we can essentially schedule them, finish the mandatory portion, and run the optional portions if the power and time allows. The challenges then becomes that how can we decide where is this imprecise boundary, because this varies. We need to decide it on the runtime instead of the compile time, and how can we schedule considering energy into account? So here, the project, what it entails that you can infer the only necessary deep neural network. So the task we are looking at is a deep neural network inference, that you can only infer the necessary layers based on the available time and energy and still get decent results without missing the deadline. So this is the first framework to demonstrate that adaptable machine learning approaches for time-aware, ultra-constrained, and intermittently power system. So think about it. If you have this deep neural network, you want to infer it, you often infer the whole thing and get the result. What we are saying that the semantic diversity of data, the available energy, and the available time can allow you can look at them and can decide to get intermediate results that are good enough, but you can get more confidence if you run the whole thing. And here we are again saying that, okay, we need to go to this dynamic imprecise boundary. How do we do that? There's 2 observations that leads towards the solution. The first is, the deeper you go into a deep neural network, the features becomes more complex and more distinguishable from each other. The second one is, all the real-world data are a combination of simple and complex samples. So here, let's say we have a roar of a tiger, a lion, and a gunshot. So the features in the first layer are sufficient enough to distinguish between a gunshot and a tiger or lion. But you need more complex feature to differentiate between a tiger and a lion, because their sound are very similar, their roars are very similar. So this makes tiger and lion roars more complex samples, while a gunshot is a more simple sample. Based on it, what we are going to do is we're going to have this framework where we execute one layer, we classify and see how is which sound was it. We do a utility test to decide Am I confident enough or not? If I'm confident enough, good. If not, I do the same thing again and again and again. And to perform this utility test, this is the interesting part come in. We cannot do a very complex utility test, which is often done in many machine learning approaches. Why? We do not have neither the energy, nor the computational power, nor the time to do so. So we have to come up with something that's very simple, but works. So let me explain that how this works. So let's look at the figure on the left. We have 3 circles, each representing a class, and a triangle that represents the sample, which we want to classify. So here, delta 2 and delta 1, that are the difference from the 2 centroids, are very similar. It means that the triangle might belong to the orange cluster or the blue cluster. I'm not confident enough. On the other hand, here, this delta 1 and delta 2 have a large difference. That means that I'm confident that this sample belongs to the orange cluster. And we can use this idea for testing the utility. And we have shown that performance using an MSP430, which is a low-power microcontroller having a microphone and a real-time clock. Along with, we have deployed our own small PCB designs that has a real-time clock that can run despite power failures. And we have seen that we have good performance. And how? So let's see, we use 4 data sets. MNIST is a digit recognition data set. ESC10 is an audio data set. Cypher is the small color image recognition data set. And a visual vector is a new data set that is more about, is there a person in the frame or not a person in the frame in a complex scenario. And we compared our approach with a no exit. So we learn all the deep neural network layers and an oracle exit. So the oracle knows I need exactly n number of layers for sample 1 and 2 number of layers for sample 2. And given that, we see that we have reduced the inference time. And we achieve similar to what a no exit system would, oracle exit system will do. But we also lose performance. Now, that is not something that is acceptable because we don't want to lose the performance just to lower the time, just to meet that deadline. Both intelligence and accurate result is as important as the deadline is. So we dig into to understand what we are doing wrong. And this is a network with a contrastive loss and Siamese network where we have 2 twin networks to train the model. And we see that, and this is how a contrastive loss works. So there's the green class samples and orange class samples. The first term of this contrastive loss tries to bring samples belonging in the same class closer together. And the second term tries to increase the distance between the samples that should be apart, that belongs to different class. So we get clusters with smaller radius but larger distance with each other. And that helps us to identify the boundary. The problem is when we were doing this early exit, there's representation is not designed to make this disjoint clusters. So we didn't know what's happening there. Solution is that we take the output of each layer and use a convex combination of a loss function, and we call it layer aware loss function. And with that loss function, we see that we still have low execution time, so we will be meeting the deadline sooner, but we are not losing the performance as much as before. So by taking into account the loss at different layers helps us to propose or to implement this early exit without losing the accuracy. Now, these are some of the techniques that we were using for approximating, so we can do computation within the timeline in the small battery-less system. But what else can be done there? So one direction of research that is very interesting is to integrate artificial intelligence more, because the current existing network, the current machine learning protocols cannot be directly used there. It's not suitable for the computation complexity, or they are not susceptible for the power failures. So deep neural network execution with research content systems, understanding how we can learn for all the data we are gathering is a big challenge. The more interesting challenge is that how we can combine the 2 communities I talked in the very beginning, the zero power communication and the zero power computing. The one of the thing that we are exploring now is called opportunistic networking, where we understand that when we can do the load balancing, when we can offload the task, or when should we offload the task. It's not about only just, oh, this data, if we upload here, it's good. It's also about how much energy I have. Can I afford sending the data? How much time it will take? Will we lose the deadline by sending the data? Or should I compute? Or is it okay, whatever performance we have is sufficient? So all this question needs to be addressed if we want to implement opportunistic networking, where we move between sending data to the edge devices or computing in these extreme edge devices. Now, this community has been so far this computing community has so far been working on on-device computing, so they were not bothered with the security at all because nothing is getting transmitted. But now, when we're talking about this partial computation, partial sending to the edge network, we have to protect how these data are. We have to protect how implement security protocols in it. And classic encryption that we are doing in traditional networking are not applicable here because, again, we do not have the computational bandwidth. So how we can implement this communication security is another big challenge to realize this vision. And that's all from me. Thank you again for listening to me, and it's a pleasure to give a talk here.
Thank you. Thank you, Basima. Thank you. So we have a few minutes before we jump right into the breakout session 1. So I know one of our speakers has had to leave early, but are there any questions for either Dr. Voles, Dr. Friesel, or Dr. Islam? Let me see. I can't actually. So maybe let's see. Just going to change the view here a bit. Oh, thank you. So any questions? So if you do, come up to the left of the podium. There's like a megaphone, green megaphone. If you stand on that, you'll be able to ask a question to everyone. We won't be able to hear you unless you're on that green megaphone. All the way at the front, right where John is, almost where John is. Any questions? John, you're getting close to the megaphone. Okay. Enough of the confetti, okay? I don't.
Alex, we do have to talk about the breakout rooms.
That's true. That's true. So it seems like, given that there are no questions, let's switch gears into breakout session time. So in terms of the schedule, like, things are a little bit shifted because of the reason is obviously, we're a little bit behind schedule, but nevertheless, what we're going to do is breakout session 1 is going to start at 3:30. We have 2 sessions in breakout session 1. We have using SDR for education. So that's with John and John Svoboda and David Starobinski.
Yes, that will be in breakout room A. Breakout room A, everyone. There's an issue with the listings right now. Just for the breakout rooms.
Yep. So and then in breakout room B, is the SDR roundtable discussions, and that's informal, getting around the table, talking about topics that the following topics that we proposed. Specifically, software-defined radio in the future of work, software-defined radio beyond radio communications, sensing, radar, and optical wireless, practical limitations and the future of COTS SDR equipment, and spectrum coexistence in the application of machine learning and AI for software-defined radio. So that's in breakout room B. So again, that starts in about 1 minute. And what I'm going to do also is I'm going to turn off, that concludes the YouTube live part of this event. So to everyone out in cyberspace watching us via YouTube, thank you again for watching. And don't forget that if anybody here wants to sort of watch again, if there's something that was really cool that was presented and such, the YouTube video doesn't disappear. So it's going to be there for forever and ever and ever. So feel free to check it out in the comfort of your own home or wherever, on the school bus, you name it. But again, that concludes this session, and looking forward to seeing you in one of the 2 breakout sessions. And of course, don't forget the networking hall with the different sponsor tables there. Like, feel free to, you're not committed to go into a breakout room, feel free to connect with folks around here. And with that, thank you, everyone. And thank you to all our Rising Star presenters.